Earth, in its silent vastness, carries a history of fragile balance and delicately interwoven cycles. For thousands of years, the planet has sustained a complex web of life that self-regulates, adapts, and evolves. However, scientists across various fields, from biology to climatology, oceanography to geology, have been identifying consistent signs that this balance is undergoing a rupture. The term ecological collapse is no longer a dramatic expression from science fiction. It is a serious hypothesis, studied with rigorous methodologies based on time series, satellite data, soil and ice samples, and advanced computational models. The natural world, once perceived as stable and predictable, is destabilizing on multiple fronts, many of them irreversibly interconnected. Over the past decades, robust evidence has accumulated that we are undergoing an ecological transition phase with large-scale collapse potential. And science, with its cold precision, is now the only reliable compass to understand this scenario. Unlike apocalyptic forecasts based on philosophical or religious assumptions, the scientific discourse on natural collapse is built on quantifiable data and replicable projections. Intergovernmental reports such as those from the IPCC, United Nations studies, publications in journals like Nature, Science, and The Lancet, all converge on the same warning. The systems that support life on Earth, such as climate, water cycles, biodiversity, and soil fertility, are undergoing accelerated transformations that surpass the natural variability observed over the last several thousand years. This is not a sudden cinematic collapse like those seen in fiction films. It is a progressive collapse, where the accumulation of micro-breaks eventually reaches points of no return. These are the so-called tipping points, abrupt transitions that, once triggered, cannot be easily reversed, even with drastic carbon emission cuts or conservation efforts. Scientists have identified at least 9 such critical points, including Arctic ice melt, Amazon rainforest dieback, collapse of the Asian monsoons, and loss of coral reefs. Each of these tipping points would be alarming on its own. But what makes the scenario even more concerning is that they are interconnected. The triggering of one can set off cascading effects in the others. Ecological collapse, therefore, is not merely an environmental event. It is a systemic phenomenon with direct impacts on climate stability, the global economy, food production, water supply, public health, and the survival of species, including our own. That is why understanding what science says about this process is not an academic or intellectual choice, but an urgent necessity. Sleeping with science, in this context, is an invitation to slow down our thinking, to dive into real knowledge, and to reconnect with the serene gravity of facts. By calmly following each of these discoveries, we are guided not by fear, but by clarity. In this script, we will be guided exclusively by data and the voices of the international scientific community. In a world saturated by noise and disinformation, the analytical silence of science becomes a beacon. In each topic, we will break down the main phenomena that indicate the weakening of the natural world, from permafrost thawing and ocean acidification to the 6th mass extinction and the collapse of food chains. All of this is based on peer-reviewed studies, robust computer models, and field observations. May this journey serve as a passage between restlessness and understanding, between urgency and serenity, between what is and what still can be avoided, or accepted with wisdom. The idea that the planet is on alert is no longer a poetic metaphor or the desperate cry of environmental activists. It is a conclusion supported by decades of data, satellite measurements, and mathematical projections. Modern science has developed increasingly precise tools to monitor the planet's health, allowing real-time observation of the deterioration of vital systems. Just as a doctor monitors the vital signs of a patient at risk, heart rate, temperature, oxygen levels, environmental scientists analyze the so-called ecological collapse indicators. Among these are biodiversity loss, species extinction rates, atmospheric concentrations of greenhouse gases, the rise in global average temperature, ocean acidity, glacier retreat, deforestation pace, and the decline of underground aquifers. Each of these metrics functions like a pointer on an invisible clock, marking the approach of a critical threshold. These indicators are not interpretive or subjective. They are observational and replicable. Global average temperature, for instance, has already risen by about the 1.2 degrees since the pre-industrial era, a figure that may seem small but signifies a colossal shift in the Earth's climate system. The safety limit proposed by scientists and international agreements, such as the Paris Agreement, is a maximum of 1.5 degrees C, because exceeding this threshold exponentially increases the risk of triggering tipping points. Another alarming metric is the current extinction rate, which is 100 to 1,000 times higher than the natural background rate observed over the last millions of years. This equates to losing dozens of species per day, many of which have not even been identified by science. In the oceans, data shows a decline of up to 40% in phytoplankton. In some regions, microscopic organisms that form the base of the marine food web and are responsible for a significant portion of the planet's oxygen production. The Intergovernmental Panel on Climate Change, IPCC, the United Nations Environment Programme, UNEP, and the two Stockholm Resilience Centre are just a few of the institutions warning about the transgression of planetary boundaries. In 2009, scientists identified 9 critical ecological thresholds that should not be crossed: climate, biodiversity, nitrogen and phosphorus cycles, land use, freshwater use, ocean acidification, ozone layer integrity, chemical pollution, and atmospheric aerosol concentration. In recent reports, at least 6 of these boundaries have already been breached, meaning we are operating outside the safe zone for human civilization. Unlike external threats, such as asteroids or pandemics, these dangers are generated and amplified by human activity, progressing at a rate that outpaces the regenerative capacity of ecosystems. The term ecological clock is often used to describe this invisible countdown. Each passing year adds more data, and the graphs continue to climb, but global response remains insufficient for the urgency reflected in the numbers. The timeline of science is continuous, but the pace of public policy is intermittent, and the timeline of nature is finite. That is why scientists around the world are increasingly relying on predictive models, computer simulations that forecast future scenarios based on current data. These models do not predict exact dates for collapse, but reveal highly probable trajectories if there is no structural transformation in our relationship with natural systems. Behind the curves, spreadsheets, and graphs lies the realization that the planet is emitting vital signs in a state of emergency. These signals are not futuristic, they are happening now. The prolonged drought of major rivers, wildfires in historically wet regions, intensified cyclones and hurricanes, the disappearance of ancient glaciers, and the salinization of arable land are concrete manifestations of a system out of balance. Most troubling is the fact that all these phenomena interact, reinforcing each other's impact. Recognizing the existence of this ecological clock is the first step in understanding the nature of the collapse that is approaching. It will not come from a single catastrophic cause, but from the sum of minor breakdowns, invisible feedback loops, and accumulated human decisions over time. And as silent as it may seem, the ecological collapse has already begun, not as an event, but as a process. Sleeping with science in this case is an invitation to awaken to the data and realize that nature's time is quietly running out under the watchful eye of science. Beneath the vast Arctic plains lies a layer of permanently frozen ground known as permafrost, a frozen soil that covers nearly a quarter of the northern hemisphere, stretching across regions of Canada, Alaska, Siberia, and Greenland. This soil is not merely an inert mass of frozen earth, it functions as a massive time capsule, preserving not only fossils, dormant viruses, and millennia-old organic structures, but also one of the most feared elements in climate science, methane. When permafrost begins to thaw, a process extensively documented over recent decades, it releases this gas, trapped in bubbles and frozen organic matter. And methane is about 80 times more potent than carbon dioxide in terms of global warming during the first 20 years after its release. Studies conducted by researchers from the Polar Research Institute, NASA, NOAA, and universities like Harvard and Stanford show that the Arctic region is warming 4 times faster than the global average. This phenomenon, known as Arctic amplification, is accelerating the thawing of permafrost at an unprecedented rate. Field measurements reveal that in many areas, soil that should remain frozen year-round is already experiencing deep summer thaws creating collapsed valleys, sudden erosion, and thermokarst lakes. Additionally, as it thaws, organic matter previously preserved for millennia begins to decompose, feeding microorganisms that produce even more methane and carbon dioxide. This creates a vicious cycle. The more the permafrost melts, the more gases are released, further warming the climate and accelerating the thaw. The central issue for climate science is that this process constitutes a positive climate feedback, a mechanism that reinforces and intensifies itself. IPCC computational models indicate that if the thawing continues at current levels, up to 70 billion tons of carbon-equivalent gases could be released into the atmosphere in the coming decades, an amount that could nullify decades of global mitigation efforts. And unlike industrial or vehicular emissions, these natural emissions cannot be regulated by public policy, laws, or technology. Once initiated, they follow the natural metabolic course of the soil, becoming one of the greatest climate risks beyond direct human control. Another lesser discussed aspect is that permafrost also harbors ancient microorganisms, viruses, and bacteria that could be reactivated by warming. In 2016, for instance, an anthrax outbreak struck Siberia following the thaw of a contaminated reindeer carcass. This possibility, though rare, is taken seriously by virologists and paleomicrobiologists who study how thawing could release ancient pathogens to which humanity has no immunity. The release of methane and the biological reactivation of ancestral organisms are two sides of the same phenomenon. The frozen ground is awakening, and what emerges from it could profoundly alter the planet's ecological and sanitary stability. Studies using satellite sensors and specialized drones show that in several regions of Alaska and Siberia, spontaneous methane emissions are already visible through infrared spectroscopy, forming giant bubbles in lakes and even deforming the soil with structures known as pingo bursts, a kind of sudden eruption caused by underground gas accumulation. This makes clear that the collapse of permafrost is no longer a future hypothesis. It is happening now, in full view of scientific instruments. And as global warming progresses, these regions act as massive emitters of greenhouse gases, silent, continuous, and impossible to contain. The thawing of permafrost, therefore, is not merely a regional Arctic event. It is one of the main triggers of planetary climate collapse. Its impact transcends borders, governments, and environmental policies. It represents the moment when the planet begins to generate its own greenhouse gas emissions beyond human control. Sleeping with science at this stage means understanding that the deepest risks are not the most visible, nor the most spoken of. They are the ones occurring beneath the surface, in the icy silence of ancient soil that is ceasing to be ice and beginning to breathe ancient, invisible, and powerful gases. For the past 12,000 years, Earth has experienced a rare period of climate stability known as the Holocene. It was this stability that enabled the emergence of agriculture, the flourishing of civilizations, and the large-scale development of human life. Global average temperatures remained within a relatively narrow range. Rainfall patterns followed predictable rhythms and natural cycles, such as monsoons, seasonal glacier melt, and soil fertility, maintained a consistency that seemed eternal. This phase of equilibrium was not the norm in Earth's history. On the contrary, it was an exception. Before the Holocene, the planet endured unstable ice ages, abrupt temperature shifts, and periods in which life struggled to persist. But in recent millennia, this ecological calm created the perfect stage for the construction of the human world. Science shows that this era of stability is coming to an end. Since the Industrial Revolution, and with increasing intensity in recent decades, human interference has begun to alter the planet's key climate regulators. Excess greenhouse gases in the atmosphere, caused by fossil fuel combustion, deforestation, and industrial practices, have rapidly increased global temperatures. Simultaneously, other aggravating factors, such as intensive urbanization, large-scale agriculture, and ocean acidification, have compromised the planet's natural buffering systems. The Holocene is gradually being replaced by a new geological epoch proposed by scientists, the Anthropocene, the era in which human activity has become the dominant geological force. This transition from one epoch to another is far more than an academic concept. It represents a structural change in the planet's climatic behavior. with profound effects on the predictability and adaptability of ecosystems. Studies published in recent decades show that we have already surpassed the thermal stability point that sustained the Holocene. The warming observed today is faster than any recorded in the past 100,000 years. The concentration of carbon dioxide in the atmosphere has exceeded 420 parts per million, a level not seen in nearly 4 million years. And the pace of this change is so rapid that neither natural ecosystems nor human cultures can keep up. One of the main consequences of this new instability is the breakdown in the predictability of regional climate systems. Rainfall regimes that once supported traditional agriculture in many parts of the world are becoming erratic. The frequency of extreme weather events, such as heat waves, droughts, floods, and hurricanes, has increased significantly, challenging the response capacities of governments, cities, and populations. The oscillation of the Faubreiter jet stream, a high-speed air current that influences weather patterns in the northern hemisphere, has become more erratic, bringing abnormally harsh winters to some regions and devastating summers to others. This instability is a direct result of thermal imbalance between the Arctic and the equator, caused by melting polar ice caps. The end of Holocene stability also threatens humanity's adaptive capacity. Many of our infrastructures, from dams to healthcare systems, were designed based on climate stability forecasts that no longer apply. Coastal cities are increasingly vulnerable to sea level rise. Forests are more exposed to pests and wildfires. Mountain ecosystems, once considered natural refuges, are losing their unique characteristics as temperature zones shift upward. Even regions once considered safe, such as temperate agricultural belts, are experiencing heat waves that undermine crop yields. In climate science, this loss of stability is often illustrated through exponential curves, tipping points, and no-return scenarios. But beyond the graphs, it represents a rupture in the unwritten contract between humanity and Earth's climate. A contract that for thousands of years allowed communities to settle, cultures to thrive, and life cycles to be passed on across generations. Now that contract is being torn apart by a silent force, fed by the sum of our collective choices and our refusal to heed the signs. To understand the end of Holocene stability is to realize that ecological collapse is not an external event, but the logical outcome of ongoing processes. It is not a natural punishment, but a systemic reaction to excessive disruptions. Sleeping with science at this point means accepting that time is changing, not seasonal time, but deep time, the kind that shapes life, and that by breaking the millennia-old balance that sheltered us, humanity has entered uncharted territory, where margins for error are shrinking and the urgency for understanding is growing. The web of life on Earth is built with such delicate complexity that the absence of a single species can reverberate throughout the entire ecological structure. This interdependence among organisms, known as biological interconnectedness, is one of the foundational pillars of modern ecology. In a healthy ecosystem, species of plants, animals, fungi, and microorganisms are linked by food chains, chemical interactions, symbiosis, and behavioral relationships. When one of these species disappears, the consequences go far beyond the individual loss. They trigger cascading effects that compromise the balance and resilience of the entire system. Science has documented these effects in natural environments around the globe. From coral reefs to tropical forests through savannas, wetlands, and tundras, ecological collapse, therefore, does not happen in isolation, but as a systemic breakdown, where the absence of one element causes the whole structure to lose support. One emblematic example involves keystone species, organisms that play a disproportionately important role relative to their population size. A classic case is the wolf in the Yellowstone region of the United States. When the species was eradicated in the 1920s, deer populations grew unchecked, destroying riverside vegetation. This led to increased erosion, disrupted bird migration, and altered insect populations. After wolves were reintroduced in the 1990s, the entire ecosystem began to recover. This phenomenon, known as a trophic cascade, reveals how apex predators regulate the food web and structural integrity of a biome. The extinction of such a species does not only affect the lower levels of the food chain, but alters the physical landscape, energy flows, biodiversity, and even the behavior of other species. Another critical case is that of pollinators, such as bees, moths, and bats. Their rapid decline, caused by pesticides, habitat loss, and climate change, directly impacts the production of fruits, vegetables, and seeds. The United Nations Food and Agriculture Organization, FAO, estimates that around 75% of global food crops depend on animal pollination. The absence of these organisms can lead to food shortages, economic disruption, and more profoundly, the collapse of other species that depend on these plants for survival. It's a chain reaction. Fewer pollinators mean fewer plants mean fewer herbivores mean fewer predators. The web quietly unravels. In the oceans, cascading effects are also precisely documented. Coral loss, driven by warming and acidification, leads to a reduction in species dependent on reef habitats. This affects fisheries, coastal protection, and even water oxygenation. The disappearance of predators like sharks or orcas also causes imbalances. Mid-level fish proliferate, overconsuming plankton or small mollusks, and collapsing the food web's foundation. In freshwater ecosystems, the extinction of frogs and toads, which serve as natural insect controllers and biological indicators of water quality, has been linked to increased disease vectors like dengue and signals the deterioration of aquatic systems. The problem becomes even more critical when cascading effects overlap. The extinction of a plant species may lead to the extinction of specialized insects, which in turn affect birds that feed on them, altering predator behavior and so on. Our study, published in the Proceedings of the National Academy of Sciences, demonstrated that species loss exponentially accelerates an entire ecosystem's vulnerability to external disturbances like droughts or wildfires. And most alarmingly, these effects are often irreversible, as the ecological niches left behind by extinct species cannot always be filled by others. The ecological function is lost, and with it, stability. Science also shows that we don't need to lose entire species to cause cascading effects. The drastic reduction of populations, known as defaunation, is enough to impair ecological functioning. This is visible in tropical forests, where declining numbers of large mammals compromise seed dispersal, vegetation regeneration, and even carbon sequestration. These effects may be slow in human time, but they are profound in ecological time. And the quieter they are, the more dangerous they become. They rarely make headlines, yet they invisibly shape life on Earth. To understand cascading effects is to realize that the collapse of the natural world will not come as a single dramatic event. It will come as a sequence of accumulated absences. First, a species disappears. Then another can no longer feed. Next, a tree stops reproducing. Later, the soil loses nutrients. And thus, little by little, the ecosystem loses meaning. Even if at first glance it still appears intact. Sleeping with science at this point is to accept the depth of this interdependence. It is to recognize that there is no such thing as isolated life on Earth, and that every lost organism is like a thread pulled from a fabric that in silence begins to unravel. Over the past 500 million years, Earth has undergone 5 major mass extinctions, abrupt events during which a significant portion of the planet's biodiversity vanished in a short geological time span. These episodes were driven by extreme forces such as asteroid impacts, large-scale volcanism, or global climate shifts. The most well-known, which occurred about 66 million years ago, brought an end to the dinosaurs and marked the close of the Cretaceous period. Today, scientists increasingly agree that we are experiencing the 6th mass extinction, with one alarming difference. It is being caused not by natural phenomena, but by a single species, Homo sapiens. The current rate of species loss is tens to hundreds of times faster than the natural average. And unlike past extinctions that unfolded over thousands or millions of years, this one is happening over mere centuries and intensifying with each passing decade. Research from institutions like Stanford University, UNESCO, the Natural History Museum of London, and the IPBES, Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services, estimates that over 1 million species are currently at risk of extinction, many of which have not yet been scientifically described. This loss spans every biological kingdom: mammals, birds, reptiles, amphibians, fish, insects, fungi, and plants. Most concerning, is that these extinctions are not confined to remote or isolated areas, but also occur in urban, agricultural, and coastal ecosystems where human presence is intense. This reveals the sheer extent of human pressure on natural habitats, leaving few ecological niches untouched by anthropogenic impact. The main drivers of extinction include deforestation, the expansion of intensive agriculture, unregulated urbanization, pollution, the introduction of invasive species by humans, and, more recently, global climate change. These factors interact and compound each other's effects. A deforested area, for example, becomes more vulnerable to invasive species, suffers changes in its microclimate, loses food sources, and thereby pushes native species closer to extinction. Moreover, habitat fragmentation prevents populations from recovering, as it reduces genetic diversity and hinders migration to safer areas. Data from the IUCN Red List, the most comprehensive global biodiversity monitoring system, show that over 28% of assessed species are at risk of extinction. In certain groups, such as amphibians, the number exceeds 40%. Some iconic animals like the Javan rhino, the vaquita porpoise, and the Bornean orangutan are virtually extinct in the wild. But there are also silent and invisible losses. Insect species vanishing without ever being named, fungi essential for soil regeneration, marine microorganisms responsible for absorbing atmospheric carbon. Each of these losses weakens the planet's complexity. The concept of a sixth mass extinction is not rhetorical. It is scientifically grounded in disappearance rates, recent fossil records, comparisons with previous epochs, and computational modeling. Biologist Edward O. Wilson once estimated that we are losing around 30,000 species per year. Even more conservative estimates still place annual losses in the thousands. This pace overwhelms ecosystems' adaptive capacities and leaves no time for nature to reorganize its balance networks. And because many of these extinctions are triggered by multiple factors, such as habitat loss combined with warming and pollution, isolated conservation actions are often insufficient in the face of such systemic collapse. The sixth mass extinction is also an existential crisis. It directly threatens food systems, water security, climate stability, and the ecosystem services that sustain human life. Science reminds us that we are not spectators, but integral components of the biosphere. And when the biosphere loses resilience, so do we. Sleeping with science at this moment means accepting that extinction is not a distant concept or a niche concern. It is an ongoing, real, measurable, and documented phenomenon that affects the present, with the momentum of a future already beginning to unravel. All life on the planet depends, directly or indirectly, on a complex structure known as the food web, an interconnected system of producers, consumers, and decomposers that keeps energy and nutrient flows in constant motion. Unlike the simplified concept of a food chain with fixed linear levels, food webs are multifaceted, unstable, and highly sensitive to even minor disturbances. In recent years, scientists across multiple fields, from marine ecology to systems biology, have been documenting signs of food web collapse in various regions around the globe. This breakdown, invisible to most people, threatens not only biodiversity, but also human survival, as it directly affects fisheries, agriculture, pollination, soil health, and the functioning of the oceans. At the base of all food webs are primary producers such as plants, algae, and phytoplankton, which convert solar energy into biomass through photosynthesis. This biomass feeds herbivores, which in turn feed carnivores, and so on. When one of these elements, especially those at the base, is altered, the entire structure begins to fall apart. A particularly alarming example comes from the oceans, where satellite data and oceanographic studies show a steep decline in phytoplankton, especially in tropical and subtropical regions. This reduction, driven by rising sea temperatures, acidification, and ocean stratification, poses a systemic threat. Phytoplankton not only sustains the marine food chain, but also produces about 50% of the oxygen we breathe. In the oceans, the effects of this collapse are already unfolding regionally. In traditional fishing zones like the South Pacific and the North Atlantic, there is a steady decline in commercial species such as sardines, cod, and tuna. This phenomenon is not solely due to overfishing, but also to the collapse of the organisms that form their food base: zooplankton, copepods, krill, and small mollusks. When these organisms disappear or decline dramatically, larger fish lose their food sources, experience stunted growth, reduced reproductive rates, and eventually vanish. This cascading collapse has already been documented in coastal systems in Norway, Japan, Canada, and Brazil. On land, the pattern is similar. The loss of pollinating insects, such as bees, butterflies, and beetles, directly affects plant reproduction, which impacts herbivores like deer and rodents. Consequently, predators of those herbivores, such as foxes, jaguars, or birds of prey, also face prey shortages. This cycle results in a degraded food web and ecological simplification, which weakens an ecosystem's resilience to climate and human disturbances. In addition, habitat fragmentation hinders species' ability to move in search of food, obstructing the regeneration of essential energy flows. Recent studies published in journals like Nature, Ecology, and Evolution reveal that the loss of functional diversity, that is, the loss of species that perform unique roles in a web, is more critical than the sheer number of species lost. Even if an ecosystem retains a reasonable number of organisms, it can still be collapsing. If it lacks essential ecological functions like seed dispersal, organic matter decomposition, or pest control. And because food webs are globally integrated, collapse in one region can trigger effects elsewhere. Fish scarcity in one country can increase fishing pressure in another, creating a global cycle of cascading collapses. Another troubling phenomenon is biological homogenization, where opportunistic species like pigeons, rats, invasive ants, or resilient algae replace the specialized organisms that have disappeared. This results in simplified, unbalanced food webs with low diversity and high vulnerability to disease, pests, and environmental change. The loss of natural predators, such as large felines or birds of prey, also allows unchecked growth of herbivores or invasive species, degrading vegetation and accelerating desertification across entire regions. The collapse of food webs is therefore not just a concern for biologists or conservationists. It is a silent planetary crisis that threatens the structure of life as we know it. Science shows that when these networks collapse, restoration becomes extremely difficult, as broken links cannot be easily replaced. Each species that disappears takes with it an irreplaceable function, and the sum of those losses destabilizes entire ecosystems. Sleeping with science at this point means recognizing that the food on our tables, the air we breathe, and the water we drink all depend on an invisible yet vital network that is quietly unraveling, thread by thread. The ocean covers more than 70% of Earth's surface and is responsible for regulating the climate, absorbing excess heat, capturing a significant portion of atmospheric carbon dioxide, and sustaining an immense variety of life forms. It is a dynamic, pulsing system essential not only to marine species, but to the stability of the planet as a whole. However, scientific data accumulated over recent decades point to a troubling reality. The ocean is falling ill, and in some places it is dying. The causes of this marine collapse are multiple and interconnected. Acidification, thermal warming, chemical and plastic pollution, overfishing, and the formation of dead zones, regions where oxygen levels have fallen so low that life can no longer exist. Ocean acidification is one of the most silent and dangerous processes ever recorded by environmental science. It occurs when a portion of the carbon dioxide emitted by human activity is absorbed by the ocean's surface waters. This CO2 reacts with water to form carbonic acid, lowering the ocean's pH. Studies show that since the start of the Industrial Revolution, ocean acidity has increased by about 30%. This change directly affects calcifying organisms, such as corals, mollusks, plankton, and crustaceans, which struggle to form and maintain their shells and structures. As many of these organisms form the base of the marine food chain, their weakening undermines the entire ecosystem, including larger, economically important species like fish and marine mammals. At the same time, ocean warming has altered circulation patterns, shifting warm water masses into colder regions and destabilizing age-old ecosystems. The increase in average sea surface temperature is now precisely measured by satellites and scientific buoys. Over the last 50 years, Oceans have absorbed more than 90% of the excess heat generated by global climate change. This warming encourages the proliferation of toxic algae, reduces dissolved oxygen levels, and contributes to the phenomenon known as coral bleaching, in which corals lose their symbiotic microalgae and die. Entire reef systems, such as Australia's Great Barrier Reef, have already experienced mass bleaching events with devastating consequences for thousands of species that once thrived there. Another critical phenomenon observed by oceanographers is the formation of so-called dead zones, technically known as hypoxic areas. These are ocean regions where oxygen levels drop so low that most marine life cannot survive. These zones are expanding due to the runoff of nitrogen and phosphorus-rich agricultural fertilizers, which trigger algal blooms. When the algae die, their decomposition consumes large amounts of oxygen, creating anoxic pockets. More than 500 dead zones have now been identified in seas and lakes worldwide, including the Gulf of Mexico, the Baltic Sea, and China's coastal waters. In these areas, fish, crustaceans, and even microorganisms either die or migrate, leaving the ecosystem biologically barren. Ocean degradation is also closely linked to chemical and microplastic contamination. Substances like mercury, pesticides, heavy metals, and pharmaceuticals have been found even in deep-sea fish, while microscopic plastic particles have been detected in shellfish, deep waters, and even plankton. These toxins enter the marine food web and eventually make their way back to humans through seafood consumption. Additionally, acoustic pollution from ships, underwater drilling, and military sonar disrupts the navigation and communication of cetaceans such as whales and dolphins, affecting their migratory routes and social behavior. Science is also documenting changes in global ocean currents, such as the Atlantic Meridional Overturning Circulation, a system that regulates temperature between the poles and the equator. Its weakening could alter the climate of entire continents, affecting monsoon patterns in Asia, rainfall regimes in South America, and the frequency of droughts in sub-Saharan Africa. As the poles melt and ocean salinity declines, this thermal transport system could collapse, triggering a chain of planetary instabilities. The collapse of the oceans is therefore a systemic crisis. It threatens biodiversity, climate regulation, the fishing economy, oxygen production, and the global chemical balance. Sleeping with science in understanding this reality is to recognize that the ocean, which protected life on Earth for billions of years, is now among the most vulnerable systems on the planet. A world without healthy oceans is not only a hotter planet, but a profoundly more unstable one, with its biological foundations silently dissolving beneath the blue surface. In climatology, the concept of an extreme event refers to phenomena that fall outside historical norms, such as intense heat waves, prolonged droughts, violent floods, high-category hurricanes, unusual snowstorms, or off-season frosts. For a long time, these events were considered statistical anomalies, rare occurrences within an otherwise stable climate system. However, over the past few decades, science has recorded a qualitative shift in this pattern. The number, intensity, and duration of such events are increasing at an accelerating rate. Today, scientists no longer speak merely of extreme events, but of a new era of recurring extremes, a phase in which the abnormal becomes frequent, a new climate normal that challenges the resilience of ecosystems, cities, and human societies. Research by the IPCC, the World Meteorological Organization, and universities such as Oxford, Columbia, and Potsdam shows that global warming is directly linked to the intensification of these events. Heat waves, for instance, have become 5 times more likely case than they were before the industrial era. In 2023, the planet recorded the hottest days in history since modern measurements began. Extreme heat directly affects human health, causes thousands of deaths annually, increases the risk of wildfires, and drastically reduces agricultural productivity. In regions like Southern Europe, South Asia, and parts of North America, temperatures above 45 degrees Celsius have become common during summer, leading to energy supply collapses, crop failures, and severe impacts on urban infrastructure. The intensification of prolonged droughts is another clear sign of climate instability. As global temperatures rise, evaporation increases, soil moisture disappears more quickly, and dry spells become longer and more severe. Countries that once relied on relatively predictable rainfall such as Brazil, India, Ethiopia, and the United States, now face recurrent water crises, as with reservoirs drying up and underground aquifers being exploited to exhaustion. Water scarcity affects not only agriculture, but also urban supply, energy generation, and the very habitability of certain regions. Additionally, dry, degraded soils become more prone to desertification, creating feedback loops that further worsen the problem. At the other end of the spectrum, torrential rains and sudden floods are also becoming more frequent and intense. As the atmosphere warms, it holds more water vapor, about 7% more for every degree Celsius of warming. This means that when it rains much more. Cities like New York, Tokyo, Lagos, Mumbai, and Sao Paulo have already experienced historic floods in very short periods, resulting in severe human and material losses. These events are not merely the result of poor urban planning, but also of global shifts in precipitation patterns, driven by increased atmospheric heat and the instability of climate streams. The erratic behavior of jet streams, high-altitude wind bands that influence regional weather, has been altered by the decreasing thermal contrast between the Arctic and the equator due to polar ice melt. This change allows cold or warm air masses to drift into latitudes where they were previously uncommon. The result is climatic anomalies, such as frosts in tropical regions, extreme cold waves in temperate zones, and unseasonal heat in areas once known for cold. This instability disrupts agricultural calendars, affects bird and insect migration, alters plant reproductive cycles, and undermines the functioning of entire ecosystems. Another alarming factor is the increasing intensity of tropical cyclones, hurricanes, and typhoons. As oceans warm, they provide more thermal energy for the formation of these storms, which are becoming not only more frequent, but also more destructive. Cyclones that previously dissipated at sea now retain their strength upon making landfall, causing landslides, infrastructure destruction, loss of life, and contamination of water sources. Events such as Hurricane Dorian, Typhoon Haiyan, and Cyclone Freddy are recent examples of the destructive power these storms can reach, and how they are becoming the norm rather than the exception. This set of extreme climate events, once seen as isolated incidents, now forms a key systemic pattern of global climate instability. Science makes it clear that the planet is not just warming, it is becoming more violent in its atmospheric dynamics, with abrupt fluctuations and persistent imbalances. Sleeping with science in observing this new climate landscape means understanding that Earth is no longer a predictable system. And while extreme events become routine, the real extreme may lie in our stubbornness to treat them as exceptions, when they are in fact explicit symptoms of an unfolding collapse. The Amazon rainforest is often described as the lungs of the world, a powerful metaphor that, while technically imprecise, conveys the vital importance of this region for global climate stability. It is the largest tropical forest on the planet, covering about 5 million square kilometers, spanning 9 South American countries, with approximately 60% located in Brazil. More than just a lush landscape, the Amazon is a self-regulating and interdependent system, whose existence depends on delicate hydrological and ecological cycles. It produces much of its own moisture through evapotranspiration, releasing billions of tons of water vapor that fuel rainfall not only across the region, but over much of South America. This closed cycle sustains trees, rivers, biodiversity, and the continent's climate patterns. However, growing scientific data shows that this forest is dangerously close to reaching a point of ecological no return, a state of irreversible degradation that would cause it to collapse as a rainforest and shift into a degraded savanna. Researchers from the National Institute for Space Research, INPE, the Stockholm Resilience Center, and the University of Sao Paulo have converged on the idea that if the Amazon loses between 20% and 25% of its original forest cover, it will enter a self-perpetuating process of savannization. Currently, it's estimated that around 17% of the forest has already been deforested since the 1970s, with an additional 7% severely degraded by fires, selective logging, illegal mining, and road construction. This means the Amazon system is dangerously close to its threshold. Once that limit is crossed, the moisture cycle breaks. Fewer trees mean less evaporation, which reduces rainfall, leading to more drought, more fire, and further forest loss. Collapse then becomes a chain reaction. Savannization of the Amazon doesn't mean the entire region will turn into desert, but rather that it will lose its ability to sustain itself as a humid, tropical rainforest. It implies the gradual replacement of tall, biodiverse trees with lower vegetation, grasses, shrubs, and drought-resistant species, similar to what occurs in the Cerrado biome. This transition deeply alters the forest's ecosystem services. Carbon storage capacity declines, biodiversity plummets, and rainfall patterns in central and southern Brazil, Bolivia, Paraguay, and Argentina become more erratic. The impact goes beyond the environment. It directly affects agriculture, hydroelectric energy generation, water supply, and the frequency of extreme weather events. Studies published in Nature Climate Change and Science Advances reinforce that global warming is increasing the vulnerability of the forest, even in areas not yet deforested. Prolonged heat waves, combined with severe droughts, are making parts of the Amazon more flammable, even those that used to remain moist year-round. Satellite imagery reveals an increase in so-called underground fires, which occur even in areas not directly hit by surface flames. These events not only kill trees from below, but also release vast amounts of carbon stored for centuries in the soil, contributing to the greenhouse effect on a global scale. Another crucial point is that the Amazon is not isolated from the rest of the planetary climate system. Its collapse would disrupt atmospheric circulation patterns, alter southern hemisphere jet streams, and destabilize the thermal balance of regions such as the Caribbean and West Africa. Furthermore, losing this immense carbon sink would make it even harder to meet the goals of the Paris Agreement and curb global warming. The Amazon rainforest is home to between 10% and 15% of all known species on Earth, and its loss would be not just an environmental catastrophe, but a rupture in the very biological tapestry of the planet. Science warns that a window of action still exists. Conservation strategies, ecological restoration, and the immediate halt of deforestation could prevent the forest from crossing that critical threshold. But time is short. Feedback cycles are already underway, and global climate change is accelerating the process. Sleeping with science at this moment is to understand that the Amazon is not a local resource, nor an exotic landscape. It is a vital cog in the planet's machinery. And at the same time, it is a living warning. When limits are ignored, even the greatest biomes on Earth can vanish, not with an explosion, but with the dry silence of the last rain that never came. The planet holds two colossal polar ice caps that function as thermal mirrors, climate regulators, and frozen freshwater reservoirs. Greenland in the northern hemisphere and Antarctica in the southern hemisphere. For millions of years, these ice masses remained relatively stable, accumulating layer upon layer of compacted snow that turned into glaciers, maintaining a delicate balance between evaporation, precipitation, and temperature. However, in recent decades, that balance has been breaking at an alarming pace. The combination of atmospheric warming, rising ocean temperatures, shifting polar winds, and changes in ocean salinity is causing these regions to melt at accelerating rates, triggering one of the most concerning processes in modern climatology: sea level rise. Greenland, home to the world's second largest ice mass, has already lost over 4 trillion tons of ice since 2002, according to NASA's GRACE satellite measurements. This accounts for an approximate 1 centimeter rise in global sea level from that single region alone. Summers in Greenland are growing longer and warmer, causing surface melt that seeps into glacier crevices, accelerating fragmentation and movement toward the sea. Additionally, soot from wildfires and human activity, known as black carbon, darkens the ice, reducing its albedo, or its ability to reflect sunlight, causing it to absorb more heat and melt even faster. The feedback loop is clear. The more ice is lost, the warmer the planet gets, and the warmer it gets, the more ice is lost. In Antarctica, the signals are even more alarming. The West Antarctic ice sheet, in particular, is showing signs of instability. Glaciologists warn that colossal glaciers like Thwaites, nicknamed the Doomsday Glacier, are detaching from the rocky base that anchors them, allowing for rapid movement toward the ocean. The base of these glaciers, once kept frozen, is now being attacked by warmer ocean waters, that infiltrate beneath the ice shelves and melt them from below. This accelerates structural collapse, reduces shelf thickness, and speeds up their slide. Complete collapse of the Thwaites Glacier, according to models from the British Antarctic Survey, could raise global sea levels by up to 65 centimeters and pave the way for destabilization of other glaciers in the region. The global impact of melting ice masses is direct. Average sea levels are measurably and continuously rising, with records showing an increase of approximately 25 centimeters since the early 20th century. It may seem small, but for coastal systems, this rise is devastating. Coastal cities across continents, such as Jakarta, New York, Miami, Lagos, Venice, Bangkok, and Recife, already face chronic flooding, accelerated erosion, saltwater intrusion into aquifers, and loss of habitable land. Some Pacific islands, like Tuvalu and Kiribati, are already organizing national evacuation plans. The World Bank estimates that by 2050, more than 1 billion people will be vulnerable to rising seas, with severe social, economic, and migratory implications. Beyond the rise itself, polar melting also changes Earth's mass distribution, which can affect planetary rotation, cause localized gravitational shifts, and unevenly redistribute ocean water. This means that some regions may experience sea level rise far above the global average, while others may observe different effects. The gravitational and isostatic changes resulting from ice melt are precisely studied by geophysicists and reveal that the ocean does not behave like a uniform bathtub, but as a sensitive system responding to mass shifts. Another concerning factor is that much of the ice in Greenland and Antarctica sits above sea level. This means that when it melts, it adds real volume to the oceans, unlike floating sea ice, which is already in hydrostatic balance. If all of Greenland's ice were to melt, an extreme scenario, global sea levels would rise about 7 meters. In Antarctica's case, the potential exceeds 50 meters. While these scenarios are not expected in the short term, the fact that we are heading in that direction, however slowly, demands our full attention. Science does not operate on panic, but on trend lines, and these lines are not slowing down. Sleeping with science when understanding polar melting is seeing beyond frozen landscapes. It is recognizing that the poles are not distant or isolated. They are thermodynamic pillars of the planet. When those pillars give way, no coastal civilization remains untouched. What begins as a stream of meltwater on ice ends as an evacuated city before the sea. Ice collapse, then, is not a future. It is a process, and science, once again, is the most precise tool we have to listen to that melt, silent, yet shaping the fate of billions. For centuries, wildfires were understood as cyclical phenomena, often natural, forming part of the balance of certain ecosystems. Biomes such as African savannas, Californian chaparral, and even parts of Brazil's Cerrado evolved with periodic fire regimes, with vegetation and fauna adapted to the regeneration brought by flames. However, in recent decades, science has shown that these seasonal cycles are being profoundly distorted, giving rise to a new era of uncontrolled, devastating, and increasingly frequent wildfires. The main explanation lies not only in the growing burned area, but in the radical change of climatic conditions that fuel these fires. Extreme droughts, record heat, low humidity, intense winds, and altered vegetation composition. Fire, once a regulating force, has become an agent of environmental collapse. Research from the IPCC, NASA, Brazil's National Institute for Space Research, INPE, and climate monitoring centers like the Copernicus Climate Service reveal that the increase in wildfire frequency and intensity is directly linked to global warming. As the average temperature rises, dry periods grow longer, soil moisture disappears quickly, and vegetation becomes dry fuel ready for combustion. In many regions, this pattern disrupts normal moisture cycles, leading to megafires, events that last for weeks or months, consume thousands of hectares, and exceed human capacity to control. The examples are many. Australia in 2019, California in 2020, Greece in 2021, Brazil's Pantanal in 2020, and Siberia during several consecutive summers. All these events shared a common feature. Fire was fed by an increasingly hostile climate. Beyond human-caused ignition, such as agricultural burns or lightning strikes, the environment itself has become more flammable. Regions that historically did not experience major fires, such as the Arctic boreal forests or the tropical Amazon rainforest, have started to present intense and persistent fire outbreaks. This reveals a systemic change in vegetation structure and moisture availability, indicating that biomes not adapted to fire are entering functional collapse. In the Amazon, for instance, studies show that increased fires are linked both to deforestation and climate change. Cleared areas create dry edges that facilitate the spread of flames into the forest interior, fragmenting the ecosystem and creating a vicious cycle of degradation. The impacts of uncontrollable fires go far beyond immediate vegetation destruction. They release massive amounts of greenhouse gases, especially carbon dioxide, methane, and nitrogen oxides. It's estimated that global wildfires emit around 7 billion tons of CO2 annually, a significant portion of the planet's total emissions. Additionally, they emit aerosols and soot that deteriorate air quality, cause respiratory problems, accelerate ice melt when deposited in polar regions, and alter cloud formation. The fire cycle, therefore, is not just ecological, it is also climatic and atmospheric, directly influencing rainfall patterns, temperature, and global circulation. Science also shows that wildfires are not isolated events, but interconnected with other collapse phenomena through feedback loops. Deforestation promotes fires, fires intensify droughts, droughts feed new fires, and the carbon they emit accelerates global warming. This cycle is particularly severe in carbon-rich regions such as peatlands and tropical forests. When these areas burn, they release carbon stored for millennia, generating emissions that cannot be offset in the short term. Even burned areas that eventually regenerate may lose their ability to sequester carbon for decades, worsening the climate crisis. Another alarming aspect is the impact on biodiversity. Wildfires not only destroy entire habitats, but interrupt reproductive cycles, kill animals by smoke inhalation or extreme heat, and eliminate endemic species unable to escape or adapt. Some fires have caused local extinctions of amphibians, reptiles, birds, and small mammals. And because these fires often strike high biodiversity regions, like Brazil's Cerrado or the Amazon rainforest, the loss is irreversible. Sleeping with science at this point is understanding that fire is no longer a natural controlled phenomenon, but a direct indicator of global climate instability. The flames that consume entire forests are not accidents, they are symptoms of a hotter, drier, more fragile planet. When climate fuels fire, and fire reinforces collapse, the natural world ceases to be a refuge and becomes a combustible field. And with every fire we fail to contain, we lose not just trees and animals, but time, the scarcest resource in the face of a collapse that burns silently behind the smoke. Beneath our feet, the soil seems static and unchanging, a firm carpet upon which we build cities, grow food, and walk every day. But for climate science, ecology, and agronomy, soil is a living, dynamic, complex, and profoundly vulnerable system. Every handful of fertile earth contains billions of microorganisms, roots, fungi, minerals, gases, and organic particles that interact in a delicate balance. It stores carbon, regulates the water cycle, filters contaminants, provides nutrients, and sustains the foundation of the terrestrial food chain. Yet in recent decades, this essential system has been entering a state of collapse. The failure of the planet's soils is a silent but devastating process, with direct implications for food production, climate stability, and ecosystem health. Soil degradation occurs due to several interconnected factors: erosion, compaction, salinization, acidification, loss of organic matter, and chemical contamination. It is estimated that over 30% of the world's soils are already degraded to some extent, according to the FAO, Food and Agriculture Organization of the United Nations. In regions such as the African Sahel, South Asia, the Western United States, and parts of Brazil, the impacts are visible. Rapid desertification, agricultural crop collapses, and the loss of vegetation cover. Degradation not only reduces the productivity of the soil, but also eliminates its ability to store water and capture carbon, turning living landscapes into barren, infertile surfaces. Intensive industrial agriculture is one of the main drivers of this degradation. The continuous use of chemical fertilizers, pesticides, monocultures, and heavy machinery deeply alters the soil's structure. When soil is aggressively and repeatedly plowed, its organic matter rapidly oxidizes, releasing carbon dioxide into the atmosphere. At the same time, the underground microbial life, essential for the nutrient cycle, is destroyed, compromising long-term fertility. This production model, while it has boosted short-term yields in recent decades, is depleting the natural foundation of agriculture. Productivity may rise, but the soil becomes sick. And when soil gets sick, everything that depends on it is at risk. Climate change further intensifies this process. Intense heat waves and alternating torrential rains, both amplified by global warming, accelerate erosion and nutrient leaching. In many areas, long droughts are followed by violent rains that wash away the fertile topsoil layer known as humus. Without this layer, regeneration becomes slow or unfeasible. And since soil is the product of thousands of years of geological and biological formation, its loss cannot be replaced within human timescales. A single centimeter of fertile soil may take 100 to 1,000 years to form, but can be destroyed in just one poorly managed harvest. In addition, salinization, the accumulation of toxic mineral salts in the soil, has been affecting intensively irrigated regions, especially in the Middle East, South Asia, and parts of Latin America. The continuous use of low-quality or poorly managed irrigation water leads to salt buildup, rendering the soil unproductive and unsuitable for agriculture. This phenomenon is worsened by water scarcity, which forces farmers to use alternative and less potable irrigation sources, creating a cycle of self-degradation. Another critical point is the decline in soil biodiversity. Mycorrhizal fungi, nitrogen-fixing bacteria, earthworms, and numerous invertebrates play crucial roles in respiration, fertility, and soil structure. With chemical contamination and compaction from tractors and livestock, this subterranean fauna disappears. Without it, the soil becomes inert, losing porosity, oxygenation, and resilience. This means that even when industrial inputs are applied, the soil no longer responds with the same efficiency, leading to a spiral of chemical dependence, rising costs, and declining productivity. Science also warns of the imminent collapse of the global phosphorus reserve, a nutrient essential for plant growth and a cornerstone of modern agriculture. Unlike nitrogen, phosphorus cannot be synthesized artificially and is extracted from non-renewable mines. With soil degradation and inefficient fertilizer use, a significant portion of this phosphorus is wasted, ending up in rivers and oceans where it causes eutrophication. If soils continue losing their ability to retain and recycle nutrients, the risk of a global food crisis becomes much more real. Sleeping with science in the face of soil collapse is to understand that the literal foundation of civilization is disintegrating. It is realizing that behind the abundance of supermarkets lies a natural system in breakdown, increasingly dependent on artificial corrections that cannot replicate the complexity of underground life, and that without living soil, there is no food, no filtered water, no climate balance, only dust, silence, and the memory of a land that once flourished, until neglect turned it into desert. Fresh water, despite covering only a tiny fraction of the Earth's surface, is the most precious element for sustaining life as we know it, representing less than 2.5% of the planet's total water. The amount available for human use, excluding polar and glacial reserves, accounts for less than 1%. Yet it is this water that irrigates crops, supplies cities, sustains rivers and forests, regulates local climate, and has shaped cultures for millennia. Science has made it increasingly clear that this vital resource is entering a state of collapse. Lakes are drying up, rivers are disappearing from their historical beds, and underground aquifers are being extracted at a rate far exceeding their natural recharge. The freshwater crisis is no longer a prediction. It is a reality, already measured by satellites, hydrological models, and field data across every continent. The world's great rivers, which for millennia defined the boundaries of civilization, are now symbols of scarcity. The Colorado River in the United States no longer reaches the sea. The Yangtze River in China is facing severe droughts and record low water levels. The Tigris and Euphrates, cradles of Mesopotamian civilization, are drying at an accelerated pace, compromising agriculture and water supply in Iraq and Syria. In South America, the Paraná River Say reached its lowest level in 77 years in 2021, directly affecting energy generation and river transport in Brazil, Paraguay, and Argentina. Even the Amazon River Say, the largest by volume in the world, is showing quiet and localized signs of flow reduction during critical periods, especially during prolonged droughts intensified by climate change. Alongside the rivers, lakes and reservoirs are also shrinking. A study published in Science in 2023 revealed that more than half of the world's large lakes are losing volume. Lake Mead and Lake Powell in the US have entered critical scarcity levels. The Aral Sea, once one of the largest bodies of water on Earth, has lost more than 90% of its surface area. Lake Urmia in Iran has almost vanished. These hydrological collapses not only affect aquatic flora and fauna, but also create zones of local climate instability, increase aridity, reduce irrigated agriculture, and force human migrations. Additionally, the exposed dry areas become sources of toxic dust, contaminating the air with heavy metals and pesticide residues. More hidden, and perhaps more alarming, is the collapse of underground aquifers. These water reservoirs stored between rocks and sediments are a crucial part of global human water supply. However, they are being exploited unsustainably. In almost every agricultural nation in the world, the Ogallala Aquifer in the US has already lost up to 60% of its capacity in some areas. Northern China's aquifer is being extracted so intensely that large regions of the country are sinking, a process known as subsidence. In South Asia, the Indo-Gangetic super aquifer is being pumped at alarming rates to support agriculture in India and Pakistan. Even the Guarani Aquifer, one of the largest in the world, spanning Brazil, Paraguay, Uruguay, and Argentina, is under growing threat due to contamination from nitrates, pesticides, and disordered land use. Hydrological science shows that aquifer recharge is slow, depending on factors like vegetation cover, rainfall patterns, and soil infiltration. When more water is withdrawn than replenished, an chronic hydrological deficit forms, leading to the collapse of these invisible reservoirs. Furthermore, urbanization, paving, and soil sealing prevent rainwater from properly infiltrating the ground, worsening the loss. Excessive groundwater extraction also causes saltwater intrusion, especially in coastal areas, rendering wells unusable for human and agricultural consumption. Another aggravating factor is the high widespread pollution of water bodies. Nitrogen and phosphorus-rich fertilizers, industrial waste, untreated domestic sewage, and heavy metals contaminate lakes, rivers, and reservoirs. Eutrophication, the excessive growth of algae fueled by nutrients, depletes oxygen in the water, killing fish and creating toxic environments. Resistant microorganisms and emerging pathogens thrive in these polluted waters, increasing the risk of outbreaks of diseases such as cholera, leptospirosis, and giardiasis. This combination of scarcity and contamination leads to what the UN classifies as extreme water stress, when a country or region consumes more than 40% of its renewable water resources. Today, more than 2 billion people live under constant water stress, and that number is expected to rise in the coming decades. Sleeping with science at this point is accepting that fresh water, though abundant on the surface of the blue planet, is in reality a scarce, vulnerable, and finite resource. It means understanding that the water cycle is breaking on multiple fronts: in the springs that dry up, in the rains that become unpredictable, in the rivers that no longer reach the sea, and in the aquifers that silently collapse. And without water, there is no agriculture, no health, no civilization. Only multiplied thirsts, dry wells, and the memory that the water crisis does not scream. It evaporates. They are small, discreet, and often invisible to the hurried eye. But insects represent the most numerous and functionally diverse group of organisms on Earth. It is estimated that there are over 5 million species of insects, although only about 1 million have been formally described by science. They are pollinators, decomposers, natural predators of pests, food for birds, reptiles, and amphibians, and they contribute directly to soil fertility and ecological balance. They are, therefore, fundamental gears of the biosphere. Yet science has revealed a disturbing fact. Insects are disappearing on a global scale, rapidly, silently, and systematically. Not due to a single catastrophic event, but through the accumulation of pressures that together represent one of the gravest and most overlooked collapses of our time. Studies such as the one published in Biological Conservation in 2019 indicate that more than 40% of insect species are in decline, and that their extinction rate is 8 times faster than that of mammals, birds, and reptiles. In terms of biomass, some regions in Europe and North America have recorded losses exceeding 75% in less than 30 years. These data come from standardized traps, long-term monitoring, and reliable historical series. The decline is not limited to a few charismatic species, like bees or butterflies, but affects the entire group: beetles, wasps, moths, dragonflies, crickets, cicadas, ants, and countless others. It is an invisible erosion of life, often without headlines, but with systemic consequences for all terrestrial and aquatic ecosystems. Among the main causes, science highlights habitat loss, driven by urbanization, intensive agriculture, and deforestation. Landscapes that were once rich mosaics, with forests, fields, watercourses, and transitional zones, are being replaced by vast monocultures, chemically treated pastures, and impermeable surfaces. This homogenization destroys insect ecological niches, reduces food sources, hinders reproduction, and breaks migratory routes. Additionally, the intensive use of consystemic pesticides, such as neonicotinoids, impairs the central nervous system of insects, even at sublethal doses. These compounds are persistent, water-soluble, and found in pollen, nectar, and the vegetation of crops, making the environment hostile even for species not directly targeted by spraying. Climate change also plays a crucial role in this decline. Shifts in temperature and humidity affect insect life cycles, desynchronizing them from their food sources. For example, flowers that used to bloom at specific times now open earlier or later, becoming out of sync with pollinators' reproductive calendars. Heat waves, wildfires, and prolonged droughts reduce the availability of essential microhabitats like hollow logs, ground vegetation, moist soil, or natural cavities. Many insects with short life cycles and limited dispersal capacity cannot migrate or adapt quickly enough, resulting in localized and eventually regional population collapses. Another alarming factor is light and noise pollution. The spread of artificial lighting in urban and rural areas disrupts moth navigation, firefly reproduction, and the behavior of many nocturnal insects. Meanwhile, constant noise from engines, roads, agricultural machinery, and cities interferes with communication and orientation in species that rely on specific sounds for mating or locating themselves. Though less publicized, these issues form a growing field of study known as car-sensory pollution, a new frontier in collapse ecology. The extinction or sharp decline of insects has a direct consequences for humans. Pollination, essential for around 75% of global food crops, is endangered by the disappearance of bees, flies, wasps, and other natural agents. Fruits, vegetables, grains, and oil seeds depend on this free ecosystem service, which cannot be fully replicated by artificial technologies. Moreover, without decomposer insects, nutrient cycles are disrupted. Organic matter doesn't break down properly, soils lose fertility, and carbon accumulates. Without insects at the base of the food web, hundreds of species of birds, amphibians, and small mammals lose their primary food source, collapsing entire trophic networks. Science warns that the disappearance of insects is not an isolated phenomenon, but an early sign of ecological collapse. They are environmental sentinels, small but vital. Their silence is a warning of a world becoming biologically poorer, less resilient, and more prone to systemic failure. Sleeping with science in this context is to hear what is no longer audible. The missing buzz, the flight that never came, the flower left unfertilized. And to understand that without these tiny engineers of nature, the world becomes a sterile place, where even the wind blows quieter, through leaves that no longer tremble and fields that no longer bloom. Cities, hubs of human activity, commerce, mobility, and culture, are also zones of accelerated climate transformation. The way they are structured, with concrete, asphalt, glass, and steel, creates conditions vastly different from those found in natural environments. This phenomenon is known as the urban heat island effect, and it turns metropolitan areas into localized thermal bubbles, where temperatures can be between 3 degrees and even 12 degrees Celsius higher than surrounding rural areas. As the planet warms, these bubbles are becoming increasingly hostile, not only to humans but also to urban biodiversity, public health, and the stability of local microclimates. Science has shown that modern cities not only trap heat, they can prevent its dissipation, creating an artificial climate that intensifies the ecological risks already unfolding. The physical mechanism behind heat islands is simple and measurable. Urban materials like concrete and asphalt absorb far more solar radiation than natural surfaces such as vegetated soils, bodies of water, or forests. During the day, these materials heat up rapidly. At night, they release the stored heat slowly, preventing natural cooling. Additionally, the vertical design of buildings hinders air circulation, while the lack of green spaces reduces evapotranspiration, a key process in thermal regulation. The result is a stifling urban microclimate that intensifies year after year. NASA satellites have already identified urban centers that behave like true thermal pans, with surface temperatures up to 20 degrees C higher than surrounding vegetated areas. This excess heat has immediate ecological implications. Urban insects, birds, reptiles, and small mammals are directly affected by elevated temperatures. Many of them have narrow thermal tolerance thresholds, especially during early life stages. Extreme heat can prevent egg hatching, disrupt reproductive cycles, disorient migration routes, and drastically reduce the availability of food and shelter. Some species adapted to urban environments, such as swallows, solitary bees, and frugivorous bats, have shown consistent population decline, even in cities that still maintain fragmented green areas. Urban ecology acknowledges that metropolitan centers are becoming inhospitable even to life forms that once resisted concrete. Beyond biodiversity, humans suffer directly from the physiological consequences of trapped heat. Rising nighttime temperatures interfere with restorative sleep, increase the risk of cardiovascular and respiratory illnesses, and trigger outbreaks of infections. Prolonged heat exposure is also linked to neurological problems, dehydration, and the worsening of chronic conditions, particularly among the elderly, children, and outdoor workers. Hospitals in major cities already report emergency surges during heat waves, a phenomenon that is expected to become more frequent. The World Health Organization warns that by 2050, over 250,000 annual deaths could occur due to heat-related causes, most of them in urban areas poorly equipped to handle extreme temperatures. The lack of urban vegetation also undermines the climate resilience of cities. Trees provide more than shade. They function as biological water pumps, regulating humidity, absorbing air pollutants, and promoting local cooling through transpiration. When trees are removed, for construction, road expansion, or due to lack of planning, cities lose one of their natural climate defense systems. Studies show that urban green coverage can reduce a neighborhood's average temperature by up to 5 degrees Celsius, while also contributing to psychological well-being, lowering violence, and improving air quality. Soil sealing, another hallmark of modern cities, blocks rainwater infiltration, causing flooding, erosion, and pollution of urban rivers. Combined with extreme heat, this process leads to the collapse of urban microecosystems. Plants wilt rapidly, aquatic species are poisoned by chemical runoff, and birds abandon areas in search of less aggressive environments. The result is a widespread biological impoverishment that turns urban areas into ecological deserts, places where life persists only at high energetic and biological costs. Sleeping with science, when understanding the phenomenon of urban thermal bubbles, means recognizing that cities have become condensed models of global climate collapse. They don't just reflect warming, they amplify, distribute, and accelerate it. The way we build our collective space is directly tied to how the planet responds. And when heat can no longer escape, neither through concrete alleys nor suffocating skies, it accumulates not just in the environment, but in our failure to recognize that the solution to collapse lies not in the walls we erect, but in the nature we remove. Human health has always been connected to the environment, but in recent decades, this connection has become more fragile, more dangerous, and more apparent. Science has shown that changes in natural ecosystems and the global climate are creating ideal conditions for the emergence of new infectious diseases, many of them zoonotic in origin, meaning they are transmitted from animals to humans. As habitats are destroyed, species are forced to migrate, and climate patterns become unstable. Pathogens find new routes, new hosts, and new territories. Ecological collapse is reshaping the map of epidemics, accelerating viral mutations, and increasing the risk of climate-driven pandemics. Global outbreaks triggered or worsened by environmental imbalances, according to studies published in journals such as Nature, The Lancet Planetary Health, and reports by the World Health Organization, WHO. Over 60% of emerging infectious diseases are zoonotic, and many are linked to biodiversity loss, deforestation, and the wildlife trade. When ecosystems are fragmented, species like bats, rodents, and primates, natural reservoirs of viruses, lose their habitats and come into direct contact with humans or domestic animals. This contact creates opportunities for viruses to jump between species, a phenomenon known as spillover. COVID-19, Ebola, SARS, avian flu, and HIV are all examples of zoonoses with massive impacts, each in some way tied to environmental degradation and human encroachment on natural habitats. Climate change also plays a decisive role in the geographic expansion of disease vectors. Mosquitoes like Aedes aegypti, which transmit dengue, Zika, chikungunya, and yellow fever, are spreading to higher latitudes and altitudes due to rising average temperatures. Regions once too cold for these vectors now offer ideal conditions for their reproduction. This means that tropical diseases could become common in temperate countries, affecting populations unprepared in terms of infrastructure, immunity, and public response. The same applies to ticks that carry Lyme disease, which are expanding their range in the United States and Europe. Changes in rainfall patterns, frequent floods, and intense heat waves also promote outbreaks of waterborne and foodborne diseases, such as cholera, giardiasis, hepatitis A, and acute diarrheal diseases. Water contaminated by sewage or industrial waste, especially after floods, becomes a vector for epidemics that disproportionately impact vulnerable populations. In refugee camps, slums, and urban peripheries, the combination of heat, humidity, and lack of sanitation creates biological incubation zones where outbreaks spread quickly. Furthermore, global warming could reactivate ancient pathogens preserved in frozen soils or permafrost, such as anthrax, smallpox, or multi-drug-resistant bacteria. The melting Arctic has already exposed carcasses of infected animals and viral strains dormant for centuries. Another worrisome aspect revealed by science is the rise of antimicrobial resistance. The widespread use of antibiotics in agriculture, combined with the dumping of pharmaceutical waste into rivers and soil, creates environments that favor the selection of old bacteria resistant to conventional treatments. On a warmer planet, these bacteria reproduce faster, become more virulent, and gain ground in healthcare systems. This means common infections could become deadly, as current medications lose effectiveness. The WHO already considers antimicrobial resistance to be one of the top 10 global public health threats. The COVID-19 pandemic served as a preview of what scientists call interconnected epidemiological shocks, when health, environmental, and economic crises feed into one another, amplifying their global impact. Lockdowns briefly reduced emissions, but also revealed the vulnerability of our global supply chains. At the same time, they highlighted the need for more robust health surveillance systems integrated with environmental and climate data. Research centers like EcoHealth Alliance, the One Health Institute, and the Planetary Health Alliance advocate that human, animal, and ecological health must be treated as one, through an integrated, preventive approach grounded in data and international collaboration. Sleeping with science in this context means recognizing that the emergence of diseases is neither accidental nor divine punishment. It is a direct result of a planet in imbalance, where boundaries between species, habitats, and climates are dissolving. Every fallen forest, every displaced animal, every contaminated lake opens another breach through which the invisible becomes real, the local becomes global, and biology becomes crisis. And if we ignore the warning signs from the planetary body, we may be forced to heed the symptoms in the form of fever, breathlessness, and isolation. Science may not predict the next virus with precision, but it does anticipate the conditions in which it will arise. And those conditions are already taking shape. The oceans harbor a diversity of life that we are still far from fully understanding. From microscopic plankton to whales weighing dozens of tons, marine life supports not only the planet's ecological balance, but also the food supply of billions of people. However, scientific data shows that life in the seas is collapsing, not only because of climate change, acidification, or pollution, but due to a direct, measurable, and human-driven cause: predatory fishing and industrial overexploitation. Entire species are being pushed to the brink of extinction, oceanic food chains are being dismantled, and fish stocks that once seemed inexhaustible are now nearing collapse. The United Nations Food and Agriculture Organization, FAO, estimates that more than 35% of global fish stocks are currently overexploited, while another 60% are fished at their maximum sustainable limit. This means that only a tiny fraction of fish populations worldwide remain in balance. Commercial species like cod, bluefin tuna, flounder, shrimp, and anchovy are undergoing severe population declines, often with no time to recover. The speed of industrial fishing, combined with technologies like sonar, bottom trawling nets, long lines with hundreds of hooks, and massive refrigerated fleets, has turned the ocean into a zone of unrelenting extraction, where the logic of natural renewal has been replaced by the logic of exhaustion. Bottom trawling, in particular, represents one of the most destructive fishing methods ever recorded. These nets scrape the seafloor across hundreds of kilometers, destroying fragile habitats like coral reefs and sponge fields, while indiscriminately capturing thousands of unwanted species, known as the bycatch. It's estimated that around 40% of the global catch is discarded dead uncontrollable, having no commercial value. This invisible slaughter includes dolphins, sea turtles, sharks, rays, seabirds, and even endangered species. In some regions, like the Western Indian Ocean and the South Atlantic, bycatch outweighs the targeted catch. It is a silent collapse, where death is measured not in species, but in tons of lost life. The collapse of marine life is also directly tied to the destruction of natural nurseries, such as mangroves, estuaries, and seagrass meadows. These coastal ecosystems are critical for the reproduction and growth of juvenile fish, providing shelter and food for thousands of species. Yet urban expansion, chemical pollution, and industrial waste dumping are compromising their integrity. The loss of mangroves, for instance, reduces natural storm protection, increases coastal erosion, and eliminates key feeding and breeding areas for crustaceans and fish. Without these habitats, the ocean's regenerative capacity collapses. Science also warns of the phenomenon known as fishing down the food web. As large predators, such as tunas, sharks, and groupers, are eliminated, the industry turns to smaller and younger species, drastically reducing the average size of fish caught. This shifts the entire trophic structure of the ocean, fostering imbalance among algae, herbivores, and small predators. In some cases, like the Black Sea, this dynamic has led to the proliferation of jellyfish and opportunistic organisms, turning diverse ecosystems into biologically impoverished systems. The social impact of this collapse is profound. For more than 3 billion people worldwide, especially in low-income coastal countries, fish is the main source of animal protein. The decline of artisanal fishing, caused by unfair competition from large industrial fleets, worsens poverty, increases food insecurity, and destroys traditional cultures tied to the sea. In some cases, entire communities abandon centuries-old activities due to fish scarcity, relocating to precarious urban centers and intensifying social problems. Marine overexploitation, therefore, is not just an environmental issue. It is a food, economic, and cultural crisis with global implications. Sleeping with Science in the face of marine collapse, is recognizing that the ocean is not limitless. It's understanding that every school of fish caught beyond the limit, every reef destroyed by trawling, every net cast without regulation pushes the planet closer to a point of no return. The sea, which for ages nourished, connected, and inspired humanity, now bleeds in silence under the weight of indifference and short-term profit. And if there is no restraint, the ocean we know will become a sterile blue surface, beautiful on the outside, empty within. Science shows that regeneration is still possible, but the time of abundance is gone. For millions of years, Earth's biogeochemical cycles functioned as self-regulating systems in which nutrients like nitrogen and phosphorus circulated in balance among the biosphere, lithosphere, atmosphere, and hydrosphere. These elements are essential for life. Nitrogen is a component of amino acids, proteins, and DNA, while phosphorus is found in ATP, the fundamental energy molecule of cells, and in the structure of bones, teeth, and cell membranes. However, science has shown that in recent decades, human interference in these cycles has exceeded all natural limits, generating one of the most insidious and silent forms of ecological collapse. The massive use of chemical fertilizers in modern agriculture, combined with runoff from urban and industrial waste, is destabilizing the nitrogen cycle and depleting global phosphorus reserves, with severe and lasting consequences for both terrestrial and aquatic ecosystems. The Green Revolution, which began in the second half of the 20th century, brought about a profound transformation in global agricultural production through the introduction of hybrid seeds, intensive irrigation, and synthetic fertilization. One of its main pillars was the use of nitrogen fertilizers, industrially produced through the Haber-Bosch process, which converts atmospheric nitrogen into ammonia usable by plants. While this process increased crop yields, it also quintupled the amount of reactive nitrogen on the planet. Most of this nitrogen, however, is not absorbed by cultivated plants. It runs off into rivers, lakes, and oceans, where it causes severe ecological imbalances. This excess nitrogen triggers a phenomenon known as eutrophication, the abnormal enrichment of water bodies with nutrients, leading to the proliferation of microscopic algae. When these algae die, their decomposition consumes large amounts of oxygen, creating dead zones where most aquatic life cannot survive. Entire regions such as the Gulf of Mexico, the Baltic Sea, Lake Erie, and Chesapeake Bay face seasonal oxygen collapses that impact fish, crustaceans, mollusks, and local fisheries. The combination of nitrates and heat also promotes the emergence of toxic cyanobacterial strains, capable of producing neurotoxins and hepatotoxins that affect animals, humans, and even the air around contaminated waters. Phosphorus, meanwhile, presents a different but equally alarming dilemma. Unlike nitrogen, which can be synthesized industrially from the air, phosphorus is extracted from finite geological deposits, located in only a few countries, such as Morocco, China, and the United States. It cannot be artificially manufactured, and its large-scale mining is associated with ecosystem destruction, heavy metal contamination, and geopolitical conflicts. It is estimated that, at the current rate of use, exploitable phosphorus reserves will run out within 50 to 100 years. Without phosphorus, large-scale agriculture is impossible. This means that global food security depends on a resource being used with extreme inefficiency. Only a small fraction of the phosphorus applied actually reaches plant roots. In addition to waste, much of the phosphorus is lost through surface runoff, also contributing to eutrophication of water bodies, especially in tropical and subtropical regions. Phosphorus pollution has caused blooms of toxic algae in human water reservoirs, making the water unfit for consumption and requiring expensive, complex chemical treatment. Phosphorus also accumulates in the soil unevenly, hindering the growth of certain plants while favoring invasive species. This compromises biodiversity and alters ecological relationships among plants, fungi, and soil microorganisms. Human interference in these two cycles, nitrogen and phosphorus, is so deep that it has already surpassed safe planetary boundaries, according to the model proposed by the Stockholm Resilience Center. These boundaries mark thresholds beyond which Earth's stability as a habitable system may be compromised. The breach of the reactive nitrogen threshold is considered one of the most critical, as it alters the climate, water quality, atmospheric composition, and the health of aquatic ecosystems. Meanwhile, the looming scarcity of phosphorus represents a powerful strategic threat to food production, especially in countries that rely on importing this mineral. Science has proposed solutions such as reusing organic urban and human waste, optimizing fertilizer use through digital precision, intercropping, and developing phosphorus recycling technologies from sewage sludge. But these alternatives are still marginally adopted and face political and economic resistance. Sleeping with science when facing this dilemma means understanding that more ecological collapse is not caused only by visible factors like deforestation or wildfires, but also by invisible alterations in the elemental cycles of life. Nitrogen and phosphorus are nutrients of fertility, but in excess or mismanaged, they become triggers of ecological death. And when the soil is poisoned, the water turns toxic, and crops rely on vanishing elements. What's at risk is not just the environment, but the very civilization that depends on it. In an increasingly industrialized world, plastic has become omnipresent. It's found in cars, packaging, clothing, furniture, electronics, pipelines, cosmetics, and food. Its lightness, durability, and low cost have made it a symbol of modernity, and also one of the most significant agents of environmental contamination in the 21st century. What science now confirms with disturbing clarity is that plastic, as it degrades into invisible fragments, gives rise to microplastics, particles smaller than 5 millimeters in diameter that infiltrate every ecosystem on Earth, from the ocean depths to inside the human body. This contamination is not localized, accidental, or reversible. It is systemic, continuous, and universal. Studies published in Science, Nature Communications, and Environmental Pollution have shown that microplastics are present in nearly all natural and artificial environments. They have already been detected in the atmospheric air, Arctic snow, the depths of the Mariana Trench, groundwater, table salt, beer, and even in the human placenta. Tissue samples have revealed plastic particles in the lungs, liver, kidneys, blood, and breast milk. In a recent study, microplastics were even found in the brains of laboratory mice. After just a few days of exposure, this indicates that these particles can cross biological barriers and accumulate in vital organs, with consequences that are still not fully understood. The main source of microplastics is the breakdown of larger plastic waste, such as bags, bottles, fishing nets, and discarded packaging. Over time, sunlight, heat, and water movement fragment these materials into smaller particles that never completely disappear. Another major source is that synthetic fibers released from polyester, nylon, and acrylic clothing, which shed with each wash and pass through sewage systems without adequate filtration. It is estimated that a single washing machine can release up to 700,000 microfibers in one wash. These fragments flow into rivers, reach the oceans, and from there return as mist, rain, or contaminated food. In marine environments, microplastics are ingested by plankton, mollusks, crustaceans, fish, birds, and mammals. Once inside an organism, they can cause inflammation, intestinal blockages, hormonal disruption, reproductive disorders, and death. Beyond physical damage, these particles act as chemical sponges, absorbing persistent pollutants like pesticides, heavy metals, and hydrocarbons. As a result, when ingested, microplastics become vectors of bioaccumulative toxic contamination. This means that the effects do not stop at the first organism. They move up the food chain and eventually reach humans, especially through the consumption of seafood, bottled water, processed foods, and even the air we breathe. From a climate perspective, plastic also represents an emerging threat. Its production, which relies on fossil fuels, generates significant emissions of carbon dioxide and methane. As it degrades, it releases greenhouse gases that contribute to global warming. Furthermore, the presence of microplastics in the ocean may interfere with the ability of plankton to absorb carbon, weakening one of the planet's main natural carbon sequestration mechanisms. This means plastic pollution is not just a waste crisis, it is a climate, ecological, food, and public health crisis. The challenge of removing microplastics is nearly insurmountable, Unlike larger debris, these particles cannot be easily filtered or manually removed from oceans, soils, or organisms. They integrate into the environmental matrix. Science is attempting to develop biodegradable materials, more efficient industrial filters, and bioremediation methods using enzymes or specialized microorganisms. But the pace of pollution far exceeds the pace of solutions. Meanwhile, every minute, the equivalent of 1 truckload of plastic waste is dumped into the oceans, according to the United Nations Environment Programme. Sleeping with science when confronting the microplastic crisis is accepting that we are immersed in an invisible cloud of artificial particles. It's realizing that plastic is not only around us, but inside us. That the convenience of disposable packaging, synthetic fabrics, and immediate consumption comes at a cost. The chronic contamination of life in all its forms. And by ignoring this microscopic presence, we risk turning the entire biosphere into an intoxicated body, resilient, but gradually poisoned by the fragments of a progress that didn't know when to stop. For billions of years, planet Earth has demonstrated an extraordinary capacity for regeneration. Even after massive events like asteroid impacts, volcanic super-eruptions, and large-scale extinctions, natural systems have reorganized and re-established equilibrium over geological timescales. This phenomenon is known in science as ecological resilience, the ability of a system to absorb disturbances without losing its essential functions. However, recent research shows that we are entering a phase in which planetary resilience is failing. The intensity, speed, and simultaneity of human pressures on natural systems are exceeding ecological absorption limits, putting the planet at risk of abrupt and irreversible transitions. Studies conducted by scientists at the Stockholm Resilience Centre, the IPCC, and universities such as Oxford, Stanford, and Yale indicate that several key ecosystems on Earth are losing their ability to return to their previous state after environmental shocks. Tropical forests do not regenerate after repeated fires. Bleached coral reefs do not grow back even after temperatures normalize. Eutrophicated lakes remain biologically dead for decades, even without further pollutant input. This phenomenon is called ecological hysteresis, when reversing the damage is not enough to restore the system because it has already shifted into a new, degraded yet stable configuration. Resilience is not just a property of forests or oceans. It exists in soils, atmospheric cycles, microbial communities, and even in the symbiotic relationships between species. When biodiversity is lost, habitats are degraded, food chains are simplified, and natural cycles are disrupted, the system loses its shock-absorbing capacity, becoming vulnerable to increasingly minor disturbances. That is why in degraded ecosystems, a small climate shift can provoke catastrophic collapse, while in healthy systems, the same stress would be absorbed and dissipated. Scientists have identified 9 planetary boundaries that define the safe operating space for humanity. These include climate, biodiversity, freshwater use, soil integrity, nitrogen and phosphorus cycles, ocean acidification, the ozone layer, atmospheric aerosols, and chemical pollution. Currently, 6 of these boundaries have already been crossed, meaning global resilience is being systematically compromised. These limits are not rigid lines, but transitional zones. Once crossed, changes become non-linear, with unpredictable outcomes, feedback loops, and tipping points that drastically alter Earth's dynamics. A clear example of this loss of resilience is seen in the Amazon rainforest, which is already showing signs of shifting toward a savanna-like state in several areas. The same is happening in the Arctic, which melts faster each summer and reflects less sunlight, heating even further. In the oceans, coral reefs, often called tropical rainforests of the sea, are disappearing at an alarming rate, endangering not only biodiversity, but also the food security of millions. Each of these examples reveals that the planet is losing its ecological memory, the ability to recall, reorganize, and return to balance after impact. Additionally, globalization has intensified the interconnection between ecosystems, economies, and societies. This means that a breakdown in local resilience can generate cascading effects throughout the planetary system. An extreme drought in China can affect grain supplies in the Middle East. The loss of pollinators in Brazil can influence food prices in Europe. A heat wave in India can trigger crop failure and mass migration. Human resilience, therefore, is intrinsically tied to ecological resilience, and both are being tested at once. Science shows us that restoring planetary resilience requires deep, coordinated, and urgent action. It's not just about mitigating damage, but about rebuilding the responsiveness of ecosystems, restoring lost ecological functions, promoting biological diversity, and rethinking the ways we produce, consume, and relate to the environment. Technology alone is not enough. We must reduce systemic pressures such as excessive consumption, soil degradation, intensive fertilizer use, and large-scale deforestation. Sleeping with science in the face of planetary resilience failure is to abandon the illusion that nature will always find a way. It is to recognize that even age-old systems have limits, and when recovery capacity is exhausted, collapse is no longer reversible. Earth has already proven its regenerative power many times. But the question we must now face is not whether the planet will survive, but rather whether human civilization will survive the collapse of what was once called its resilient home. In the far north of the planet, the Arctic Ocean harbors one of the most climate-sensitive regions on Earth, the sea ice cap. Unlike continental glaciers, sea ice is not fixed to land. It floats on frigid waters and forms seasonally, expanding in winter and retreating in summer. This natural cycle has always existed, but in recent decades the rate of retreat has accelerated alarmingly. Arctic ice is melting faster than any other region on the planet, and scientists now warn that the polar ocean could become completely ice-free during summer within this century, possibly even before 2050, if greenhouse gas emissions continue at their current pace. Sea ice plays a crucial role in regulating the global climate through a physical process known as albedo, the ability to reflect solar radiation back into space. The bright white Arctic ice reflects about 80% to 90% of incoming sunlight, keeping the region cool and helping stabilize weather patterns across the northern hemisphere. When that ice disappears, it is replaced by dark ocean water that absorbs up to 90% of solar energy, warming quickly and accelerating residual melt. This creates a positive climate feedback loop. Warming causes more melting, which causes more warming, a cycle that spins beyond human control. Satellite data from missions like ESA's Cryosat and NASA's Earth Observing System show that the average thickness of Arctic ice has decreased by more than 50% since 1980. Moreover, multi-year ice, the type that survives more than one season, has almost vanished, replaced by younger, thinner, and less stable ice. This newer ice melts more easily, breaks apart faster under atmospheric pressure, and is swept out of the Arctic by ocean currents, speeding up the collapse. Climate models suggest that even with major emission reductions, the Arctic has already entered a critical trajectory, with record-low ice minimums occurring year after year. The disappearance of sea ice has both direct and indirect impacts on the planet. Regionally, it affects some indigenous peoples who depend on ice for hunting, fishing, and travel, and it threatens polar-adapted species like the polar bear, walrus, and Arctic fox. Globally, it disrupts an atmospheric circulation patterns, particularly the behavior of the pan-polar jet stream. This stream acts as a band of high-altitude winds that separates cold Arctic air from warmer air at mid-latitudes. As the Arctic warms and loses ice, the jet stream weakens and becomes more wavy, allowing warm air to surge northward, and intense cold waves to reach the south, as seen in extreme events across North America, Europe, and Asia. In addition, sea ice melt indirectly contributes to sea level rise by accelerating the collapse of land-based glaciers, such as those in Greenland, which lose structural and hydrodynamic support. The retreat of sea ice also opens new routes for shipping, oil extraction, and industrial activity in the Arctic, further increasing ecological stress on an already fragile region. Intensified human presence worsens pollution, disturbs ecosystems, and diminishes the resilience of one of the planet's last frontiers. Science considers the Arctic a climate early warning system because it responds quickly to environmental change and anticipates what may unfold elsewhere on Earth. When Arctic ice vanishes, it takes with it more than a frozen landscape. It carries away the planet's thermal memory, the reflection that once balanced climate cycles and held back the tipping points of chaos. Its loss is among the most visible, measurable and symbolic transformations or time of the Anthropocene. Sleeping with science in understanding the collapse of sea ice is like watching a lens fog over slowly. The reflection that once returned, light now absorbs heat. What was once a shield becomes a vulnerability, and what seemed distant and untouched during the silent stillness of polar ice reveals itself as the beating heart of the planet, weakened by repeated human choices day after day, decade after decade. As science confirms the advance of global ecological collapse, interest grows in radical technological strategies that could halt, reverse, or at least delay the most catastrophic effects of climate change. This emerging field, known as geoengineering, proposes deliberate large-scale interventions in the Earth's climate system, with the goal of reducing global warming or restoring lost functions of the biosphere. Ideas range from mass reforestation with genetically modified species to blocking part of the sunlight with stratospheric particles. However, as these proposals gain political and scientific attention, warnings also grow about their risks, limitations, and potential unintended consequences. One of the most debated forms of geoengineering is solar radiation management, SRM. This approach involves techniques to reflect part of the sun's rays back into space, artificially reducing global temperatures. A classic example is injecting sulfate aerosols into the stratosphere, mimicking the cooling effects of large volcanic eruptions. This method has been modeled by supercomputers and tested on small scales, but it is still far from being considered safe. The risks include altered monsoon patterns, reduced rainfall in tropical regions, unpredictable changes in atmospheric circulation, and severe impacts on agriculture. Furthermore, SRM does not address the root causes of climate change, such as excess CO2. It merely masks its thermal effects. This means that if SRM was suddenly stopped, the planet would suffer a termination shock, with abrupt and devastating warming. Another proposal is carbon dioxide removal, CDR, through technologies like direct air capture, DAC, biochar, iron fertilization of oceans, or controlled afforestation. In theory, these strategies could remove gigatons of CO2 over decades, restoring balance to the carbon cycle, but most of them require enormous scale, energy, and resources to have a meaningful impact. Direct air capture, for instance, is expensive, energy-intensive, and still in its infancy. Biochar, plant-derived charcoal added to soil, offers local benefits but faces logistical limitations. Ocean fertilization, which aims to stimulate algal growth that sequesters carbon, can create dead zones and disrupt marine ecosystems in unpredictable ways. There are even more controversial ideas, such as space mirrors, marine cloud brightening, and increasing the reflectivity of polar ice with artificial materials. These concepts, often originating from top universities and climate innovation hubs, face a fundamental ethical dilemma. Who gets to decide when, where, and how to alter the global climate? How can we prevent geopolitical, military, or corporate interests from exploiting these technologies for self-gain? And what happens if one country unilaterally deploys geoengineering and causes drought on another continent? Global governance of geoengineering remains weak, and many scientists warn that trying to correct climate imbalance through forced interventions could create bigger problems than the ones we're trying to fix. Beyond physical and political risks, geoengineering carries what science calls the moral hazard. The idea that by promising a future technological fix, it discourages urgent mitigation efforts in the present. Governments and corporations might delay emission cuts under the belief that some future innovation will save the planet. This weakens climate policy, demobilizes social movements, and creates a false sense of security. Yet the ecological crisis cannot be solved with engineering alone, because the collapse we face is not just technical, but civilizational. It involves consumption habits, economic structures, our relationship with nature, and deeply embedded social dynamics. Still, geoengineering research should not be dismissed. In extreme warming scenarios, It might provide temporary lifelines to prevent the collapse of key ecosystems, such as coral reefs, polar regions, or critical agricultural zones. What science proposes is an ethical, transparent, multilateral, and evidence-based use. But it also warns that the best form of geoengineering remains large-scale ecological restoration, protecting forests, restoring mangroves, regenerating soils, caring for rivers, and reconnecting humans with the natural systems they depend on. Sleeping with science, when contemplating geoengineering proposals, is to recognize the gap between the complexity of the climate and the simplicity of certain technical fixes. It is to understand that while human creativity is remarkable, it cannot replace the millions of years of coevolution between life and planet. And that in the face of the collapse to come, perhaps the deepest answer lies not in space mirrors or particles in the sky, but in the soil, in the forests, in the forgotten cycles, and in the humility to accept that the planet doesn't need fixing. It needs respect. Earth has already endured 5 mass extinctions over the past 500 million years. Each was triggered by catastrophic events, colossal volcanic eruptions, abrupt climate shifts, asteroid impacts that wiped out between 70% and 95% of all living species. After each cataclysm, the planet took millions of years to recover the lost biological diversity. Today, however, science confirms that we are living through the Keek's 6th mass extinction, and for the first time, it is not caused by natural forces, but by a single agent, humanity. Species are disappearing at a rate 100 to 1,000 times faster than the natural background rate, and it's not just iconic animals like rhinos, elephants, or tigers. It's all forms of life, from soil microbes to ocean dwellers, from treetops to coral reefs. Studies published in Science and Nature and by the International Union for Conservation of Nature, IUCN, indicate that over 1 million species of plants and animals are currently at risk of extinction, many within the next few decades. Most will vanish without ever being scientifically catalogued. The loss of biodiversity isn't limited to large, charismatic creatures. It includes pollinating insects, symbiotic fungi, soil microorganisms, freshwater fish, and pollution-sensitive amphibians. These are irreplaceable components of ecosystems, supporting essential functions such as soil fertility, water purification, pest control, and climate regulation. The cause of the 6th extinction is not singular. It is a convergence of simultaneous pressures driven by human activity. The most significant is habitat destruction, particularly through deforestation, industrial agriculture, urban expansion, and mining. Tropical forests in the Amazon, Congo, and Southeast Asia are being cleared for monocultures of soy, palm oil, and cattle, while savannas, wetlands, and coastal zones disappear under highways, dams, and real estate. Every minute, around 30 soccer fields of forest are destroyed, say states, and somewhere on Earth. Without their natural environments, species simply cannot survive. Other key drivers include the introduction of invasive alien species, which outcompete native species and destabilize fragile ecosystems, chemical pollution, which poisons water, soil, and food chains, overfishing and illegal hunting, which collapse entire populations, and more recently the climate change, which disrupts the reproductive, migratory, and feeding cycles of thousands of organisms. Many species simply cannot adapt to the accelerated pace of environmental change imposed by global warming, as seen with corals, which are vanishing at a planetary scale. The impact of mass extinction is not merely ecological, it is civilizational. The loss of biodiversity undermines food security, medicine, the economy, climate stability, and human health itself. About 75% of all crops depend on natural pollinators, such as bees and butterflies, whose populations are plummeting globally. Many of our most vital medicines, including antibiotics, painkillers, and cancer treatments, are derived from natural compounds found in animals, plants, and fungi. By destroying species, we are eliminating unique evolutionary solutions that took millions of years to develop and can never be artificially replicated. Sleeping with science in the face of the 6th mass extinction is to hear the silence spreading. It is to realize that the loss of a single species is not just a distant tragedy, but a tear in the living fabric that sustains human existence. Science offers no miraculous salvation. It shows through data and modeling that without profound changes to our way of life, Earth's biodiversity may collapse, and with it, the systems that provide the air we breathe, the water we drink, and the food we harvest. Extinction is not just a conservation issue, it is a statement about the future we choose to build and or abandon. For millions of years, life on Earth moved in step with natural cycles, the rhythms of the seasons, the pulses of the tides, the flows of nutrients, the regular migrations of species, the precipitation patterns, the dynamics of carbon, the water cycle, the processes of decomposition, and the symbiotic relationships between organisms. These are not isolated phenomena. They are interdependent systems that ensure the continuity of life. They act like ecological clocks, synchronizing growth, reproduction, feeding, chemical balance, and energy flow across the planet. Modern science now shows that these cycles are breaking down, and with them, the very rhythm of Earth is beginning to collapse. The hydrological cycle, for example, is already deeply disrupted. Climate change increases evaporation in some regions, while intensifying torrential rains in others, destabilizing patterns that once balanced rivers, aquifers, and groundwater. Lakes are drying as oceans rise, rainy regions turn arid, and deserts receive unexpected precipitation. Snow melts too early, glaciers retreat, rivers lose flow, and soil infiltration declines, affecting agriculture, biodiversity, and the water security of billions. The breakdown of the water cycle means the loss of ecological predictability, and when water loses its rhythm, everything else begins to falter. The carbon cycle, another vital pillar, is equally compromised. Human-driven emissions have added over 2 trillion tons of CO2 to the atmosphere since the Industrial Revolution. This has overwhelmed natural carbon sinks, forests, soils, and oceans, which once absorbed excess carbon. Depleted agricultural soils, deforested lands, and saturated seas can no longer perform their stabilizing role. The carbon that should slowly circulate between the biosphere, lithosphere, and atmosphere is now accumulating destructively, heating the planet, acidifying oceans, and altering atmospheric composition. The nitrogen cycle, as previously discussed, has been artificially amplified by intensive agriculture and the burning of fossil fuels. This excess reactive nitrogen directly affects plant bacterial and freshwater cycles. Similarly, the phosphorus cycle, essential to plant life, is being depleted in mines and concentrated toxically in bodies of water. When these chemical cycles collapse, the biological rhythms of species fall into disarray. Plants bloom off-season, animals migrate without finding food, pollinators lose their timing with flowers, and ecosystems fall out of sync. Moreover, the breakdown of photoperiodic rhythms, the natural cycles of light and dark to which organisms evolved, is being distorted by light pollution, altering the behavior of insects, birds, and mammals. Cities never go dark. Natural areas lose the contrast between day and night, and the biological clocks of millions of species are thrown off. Even the microbial activity in soil, which regulates decomposition, fertility, and carbon sequestration, is showing dysfunction in agricultural and urban zones. The soil loses its pulse, life loses its tempo. Science views this phenomenon as planetary desynchronization. It is as if Earth is trying to continue its ecological symphony, but with detuned instruments, torn sheet music, and missing conductors. When natural cycles lose coherence, stability breaks, and the planet enters a state of constant disturbance. This undermines not only species adaptation, but also climate modeling, agricultural production, water supply, and human health. Sleeping with science, while observing this collapse of cycles, is to understand that Earth is a living, rhythmic organism, and its illness is not only revealed in numbers, but in the irregular beats that now echo through everything. The breakdown of natural cycles doesn't appear as a sudden catastrophe. It reveals itself in subtle seasonal shifts, in untimely blossoms, in birds that never return, in absent rains, in soils that no longer breathe. But the cumulative effect is devastating. When rhythm is lost, balance dissolves, and life, thrown into disarray, moves toward collapse, not from a lack of resources, but from a lack of harmony. Contemporary ecological science understands the planet as a highly interconnected system, where every biome, every biochemical cycle, every species, and every climatic process is woven into countless others. There are no isolated collapses. When an essential component of the system destabilizes, it triggers chain reactions that ripple far beyond their point of origin. This phenomenon is known as coupled or systemic collapse, and it represents one of the greatest threats to the stability of the biosphere in the 21st century. What was once seen as separate environmental crises, global warming, biodiversity loss, ocean acidification, water insecurity, and soil degradation, is now recognized as interdependent parts of a single process of global collapse. One of the clearest examples lies in the interaction between the thawing of Siberian permafrost and the release of methane. As this ancient frozen soil warms, it emits vast amounts of greenhouse gases. This intensifies global warming, which in turn accelerates Arctic melting, reduces the planet's albedo, and raises average global temperatures. The extra heat fuels more intense forest fires, which destroy biomes, release more carbon, and diminish the capacity of tropical forests to absorb CO2. When these fires reach key regions like the Amazon, the South American hydrological cycle weakens, affecting rainfall, agricultural supply, and water flow for entire countries. The result is a system in which crises feed into each other, forming escalating cycles of instability. The same pattern plays out in the oceans. Marine acidification caused by CO2 absorption weakens coral reefs that support thousands of species. Their collapse reduces biodiversity, breaks down coastal food chains, and impacts human communities dependent on artisanal fishing. Simultaneously, the loss of phytoplankton undermines the ocean's ability to sequester carbon, worsening global warming. This warming affects ocean currents, such as the Atlantic meridional overturning circulation, which regulate the climates of the Americas, Europe, and Africa. The weakening of these currents can lead to extreme weather events, desertification, and crop failures in densely populated regions. Each link in this chain reacts to the one before and sets up the next. Biodiversity loss is another systemic trigger. The extinction of pollinators, for example, reduces agricultural productivity, increasing reliance on fertilizers, which in turn pollute rivers and lakes, creating dead zones. Food scarcity drives the expansion of farmland, causing more deforestation and habitat destruction. Deforestation disrupts rainfall, which affects reservoirs, dams, and hydroelectric power generation. Energy shortages put pressure on fossil systems, increasing emissions and exacerbating warming. One collapse triggers another, like a row of planetary dominoes falling in succession. The concept of interconnected tipping points, thresholds that activate one another, is now central to advanced climate models. Scientists warn that we are nearing multiple critical thresholds: the collapse of the Amazon rainforest, the melting of Greenland's ice sheets, the death of tropical coral reefs, and the thawing of permafrost. The simultaneous or sequential activation of these points could push the Earth system into a new climatic state, hotter, less stable, and less hospitable to life. Once triggered, this process could be irreversible for thousands of years. Sleeping with science when contemplating cascading collapses is to let go of the illusion that there is a single environmental problem that can be solved with a law, a technology, or a public campaign. It is to understand that we live in a living, interdependent web where each break reverberates throughout the whole. It is to realize there are no comfort zones in the face of systemic crisis, and that the ecological, social, economic, and political effects of this instability are already underway. When natural systems collapse together, there is no reprieve, no time to react. There is only the growing silence of what is lost until the web finally breaks, and Earth wakes up in a new state, unchosen, unplanned, and perhaps, for us, uninhabitable. Since the second half of the 20th century, humanity has entered a new geological era proposed by scientists, the Anthropocene, the epoch in which human activities became the main force reshaping the planet. Unlike previous eras defined by gradual natural changes, the Anthropocene is marked by a dizzying pace of transformation across Earth's systems. The atmosphere, oceans, soil, biodiversity, biogeochemical cycles, and even geological records now carry indelible human signatures. radioactive waste, microplastics, cement, aluminum, greenhouse gases, and sprawling urban networks. Yet while this era reveals the immense power of civilization, it also exposes its physical, ecological, and planetary limits. The growth of modern civilization has been sustained by three pillars: abundant fossil energy, continuous territorial expansion, and large-scale exploitation of natural resources. This model enabled the multiplication of food production, the rise of megacities, the manufacturing of billions of products, and the maintenance of a globally integrated economy. However, the Earth's systems that support this machinery, stable climate, fertile soils, freshwater reserves, pollinators, and predictable seasonal cycles, are not infinite. Data from the Global Footprint Network shows that humanity now consumes the equivalent of 1.7 planets per year. This means we are systematically exceeding the Earth's regenerative capacity, extracting more than it can replenish. The concept of planetary overshoot describes this overreach. We are mining minerals faster than they can form, harvesting fish before they can reproduce, deforesting faster than forests can regenerate, and emitting carbon in volumes the planet can no longer absorb. This dynamic creates cumulative ecological deficits, which manifest in biodiversity collapse, extreme climate change, water scarcity, desertification, and food insecurity. Each year, Earth Overshoot Day, the symbolic date when we exhaust the planet's annual natural resources, arrives earlier. This highlights that civilization has surpassed the planet's operational limits. The Anthropocene is not just a name for our era. It is a geological warning. It confirms that human impact is now comparable to titanic natural forces like ice ages or asteroid impacts. The difference is that this time, the force of transformation stems from economic decisions, consumption patterns, production models, and political choices. And because these decisions are centralized and cumulative, their effects manifest at a planetary scale, and with alarming speed. The Anthropocene confronts us with an inescapable truth. We can no longer separate the fate of civilization from the fate of the biosphere. We are embedded in the same closed system, and when that system fails, everything fails. Many scientists argue that we have already exceeded the safe operating space for humanity, also known as the habitable planetary space. This space is defined by biophysical boundaries that, if respected, ensure stability and resilience. However, with multiple boundaries already crossed, including those of biodiversity, nitrogen cycles, freshwater use, and greenhouse gas emissions, we are heading into zones of high systemic risk. In these zones, the likelihood of sudden, interconnected, and irreversible collapses rises sharply. Civilization may endure for a while by compensating imbalances with technology, trade, and adaptation, but no society can survive the collapse of its ecological foundation indefinitely. Sleeping with science in understanding the limits of the Anthropocene is to stop seeing collapse as a distant, sudden, and dramatic event. It is to realize that it has already begun, gradually, cumulatively, and quietly. It is found in the disappearance of bees, unseasonal rains, soil infertility, zoonotic pandemics, water exhaustion in major cities, energy instability, and forced climate migration. The Anthropocene is the era in which we have grown too large for the planet that sustains us, and perhaps the greatest challenge of our time is to rediscover how to become small enough to fit within it once more. Amid the growing number of scientific warnings, images of environmental devastation, and alarming data about global warming, much of humanity continues to live as if nothing were happening. Crowded malls, busy highways, stocked shelves, apps running, daily life seems to go on, oblivious to the severity of the ongoing ecological collapse. This phenomenon isn't mere ignorance, it's part of what scientists and thinkers call adaptive normalcy, the human ability to adjust to degraded realities, treating as acceptable what would, in other contexts, be seen as crisis or catastrophe. This adaptation, however, can become a dangerous mechanism of collective denial, rendering collapse invisible precisely as it accelerates. The human brain evolved to respond to immediate, visible, and localized threats, like predators, direct conflict, or sudden disasters. But climate change, biodiversity loss, and systemic collapse operate on a slow, diffuse, and global scale. They don't trigger the same urgency, because they have no clear face or pinpointed origin. Moreover, most transformations occur far from urban centers. Deforestation advances in the rainforest, corals die beneath the waves, soils degrade in rural areas. For those living in cities, the impacts appear diluted in the form of more expensive food, extreme heat or respiratory illness, but not as a recognizable collapse. This dissociation is reinforced by economic, political, and media structures that benefit from maintaining an appearance of normalcy. Advertising promotes compulsive consumption as a way of life. Politics often postpones structural decisions to preserve popularity or electoral interests. And the media, driven by algorithms and clicks, tends to prioritize instantly appealing topics over deep analyses of complex environmental issues. The result is a kind of numbed cognitive environment, where collapse is perceived as something bad happening somewhere, but never as an active and encompassing process already affecting every sphere of life. There is also a crucial psychological factor. Environmental collapse forces people to confront the possible end of a way of life they are emotionally attached to. Cars, meat, air conditioning, air travel, convenient packaging, each represents comfort, status, safety, or identity. Questioning them means reassessing deeply ingrained habits, which generates discomfort, denial, or even hostility. Science has documented this behavior in communities directly exposed to environmental threats, such as repeated floods or water scarcity. Often, even in the face of clear evidence of risk, people prefer to downplay, rationalize, or ignore the situation, because accepting the gravity of collapse demands changes that seem unbearable. This progressive adaptation to catastrophe is called the shifting baseline syndrome. With each generation, children grow up in a world slightly more degraded, yet accepted as normal. A child who has never seen a night sky free of light pollution or an untouched forest doesn't feel the loss of what they've never known. And so collapse advances not with alarms but with silences. It settles in the gaps of daily life, in the voids of ecological memory, in the distance between what we were once able to see and what we still do. Each decade, the baseline of normality adjusts a little lower until ruin becomes routine. Sleeping with science in recognizing the illusion of normalcy is learning to see the invisible. It is understanding that collapse is not an apocalyptic movie with explosions and escapes. It is the normalization of the unsustainable, the adaptation to a world quietly unraveling while we keep the lights on. The hardest task may not be stopping collapse, but awakening to the fact that it has already begun, and that only by facing it with clarity, courage, and compassion can we choose a different path, before the line of normalcy vanishes for good. Even in the face of ecological collapse, systemic degradation, and the transgression of multiple planetary boundaries, science still affirms that not all is lost. The window for action may be narrowing, but it is not closed. Many ecological systems, though weakened, retain resilience, the capacity to recover, adapt, and regenerate if human pressures are eased. This possibility lies at the heart of a growing scientific approach called ecological restoration, which aims not only to protect what remains, but also to actively recover what has been destroyed. It is a science of reconnection, regeneration, and reconstruction, grounded in data, local techniques, and traditional knowledge. Restoring degraded ecosystems can take many forms: reforesting deforested areas, reclaiming abandoned farmland, reviving mangroves and wetlands, cleaning up rivers, removing invasive species, reintroducing native species, and even de-urbanizing fragile coastal zones. Each well-planned action creates positive cascading effects. Soils begin to store carbon again, springs reappear, biodiversity returns, local rainfall cycles are restored, and microclimates stabilize. Studies show that restored ecosystems can recover up to 80% of their original functionality within a few decades, depending on the extent of prior damage. But restoration goes beyond planting trees. It requires restoring human relationships with nature. Agroecological models, for example, promote farming that respects natural rhythms, enriches the soil, protects water, and strengthens local communities. Cities can be reimagined with green infrastructure, living roofs, ecological corridors, and urban planning that reduces ecological footprints. Public policies can promote payments for ecosystem services, rewarding those who protect springs, care for riparian forests, or conserve pollinators. Technology also plays a role. Sensors, satellites, drones, and artificial intelligence can aid in the monitoring and adaptive management of restored areas. Science also highlights the importance of environmental justice in restoration. Indigenous peoples, traditional communities, and small farmers are often the most affected by degradation, yet also the most dedicated guardians of biodiversity. Their knowledge, practices, and connection to the land are essential for any regeneration process that is deep and lasting. Including these groups in decision-making, securing land rights, strengthening local autonomy, and respecting cultural diversity are not just ethical imperatives but strategic steps in restoring life on Earth. Though it may not be possible to return to the past, science shows that it is possible to build more livable futures. Even with rising global temperatures, there is still a significant difference between a world 1.5 degrees Celsius warmer and one 3 degrees Celsius warmer. Every tenth of a degree avoided means millions of lives preserved, species protected, and habitable regions sustained. Restoration is not the illusion of a pristine wilderness, but the creation of a new balance, less aggressive, more conscious, less extractive, more respectful of the planet's rhythms. Sleeping with science when contemplating hope in restoration is to accept the gravity of collapse without succumbing to paralysis. It is knowing that the damage is real, but that life still pulses in every seed, every emerging spring, every breathing soil. Restoration is the active choice to care. It is the collective decision to break the cycle of destruction and offer future generations, not just a surviving planet, but a living one. It is not about magical salvation, but about daily commitment, because if collapse stems from accumulated actions, restoration can also emerge from the accumulation of small gestures guided by science, sensitivity, and urgency. We have reached the final point of a journey traced not only by scientific data, but by threatened landscapes, broken cycles, vanished species, and lost rhythms. We spoke of the melting permafrost, the death of tropical forests, the collapse of food systems, the breakdown of oceanic chains, the mass extinction, the failure of natural cycles, the risks of geoengineering, and the Anthropocene as the era of excess. And now, in the face of all this, perhaps only one question remains. What does it mean to inhabit a collapsing planet and still live with dignity, awareness, and courage? The answer is not simple, and science, while offering us tools for understanding, does not offer us comfort. But perhaps we should not seek comfort, but clarity. Sleeping with science is a political, philosophical, and existential act. It means allowing the uncomfortable truths of the global ecological crisis to enter us, slowly, unfiltered. It means welcoming the discomfort that arises when we realize that the lifestyle we consider normal is, in truth, unsustainable, unequal, and destructive. And yet, choosing to remain attentive, because denial feeds collapse, silence accelerates ruin, indifference multiplies damage. Contrary to popular belief, knowledge does not paralyze, it liberates. It returns to us the dimension of reality, the sense of interdependence, the humility before life, and the possibility of conscious change. Collapse is not only physical, it is also psychic and symbolic. It forces us to rethink the idea of progress, the notion of success, the meaning of growth, the role of technology, the value of nature, the centrality of the human, and the place of ego on the planet. It breaks the illusion of control and reminds us that we are too part of a fragile, complex, and irreplaceable web. It demands we abandon the arrogance of world engineers and embrace the ethics of ecosystem caretakers, that we stop being consumers and become dwellers once again, that we trade extractivism for reciprocity, that we practice with each choice the rebuilding of a lost bond with the biosphere. Many people, when faced with this picture, ask, "But what can I do?" Science answers, a great deal. Change habits, pressure governments, protect territories, support communities, reject the culture of disposability, consume mindfully, cultivate bonds with the land, raise children for care rather than domination. But more than that, we can stand as lucid witnesses to a critical age. Lucidity in this time is resistance. It is the opposite of denial. It is a radical act of love for the earth, even when she bleeds. It is keeping our eyes open while the world sleeps at the edge of the abyss. To sleep with collapse, ultimately, is a metaphor for this era. It means accepting that we are living through an ecological twilight, but refusing to fall asleep in it. It means recognizing the growing shadow, but choosing to light small flames of action, of compassion, of restoration, of remembrance. It means preparing for what comes, not with panic, but with presence, with our feet on the ground, eyes on the horizon, and hearts committed to everything that can still bloom. Because even at the edge, Earth remains alive, and as long as she pulses, there is space to rebuild. With science, with humility, with justice, and with courage,